The lights dim across the studio as evening settles over distant mountain ranges and city skylines fade into soft purple twilight. Somewhere in the gentle transition between day and night, when the world grows quieter and minds begin to wander toward rest, science has offered us a new understanding of what lies beneath our feet. Not urgent, not alarming, but deeply fascinating in the way that only patient discovery can be. Scientists have just announced evidence that Earth's inner core, that distant sphere of compressed metal, residing thousands of kilometres below the surface, isn't quite what we've long imagined. It isn't simply a solid ball of iron, frozen under unimaginable pressure. Instead, it exists in a strange hybrid state that physicists call Superionic, a condition where the structure remains solid overall, yet light elements like carbon flow through it, like liquid threading through a rigid framework. This isn't a breaking disaster, no cause for alarm in the night. It's a peaceful science update about the planet's deep interior, about how the heart of Earth might be softer, more dynamic, and far more interesting than generations of geologists suspected. To understand what this means, we need to take a gentle journey downward through Earth's layers, starting from the surface where we stand and descending through geological strata that most of us will never see, that exist only in seismic readings and computer models, and the careful deductions of scientists who listen to earthquake waves the way musicians listen to symphonies. The Earth beneath us is structured like a nested set of spheres, each with its own character and composition. At the surface lies the crust, that thin skin of rock we walk upon, drill into, build our cities across. Below that extends the mantle, a thick layer of hot, slowly flowing rock that makes up most of Earth's volume, moving at speeds measured in centimetres per year, driving the slow collision and separation of continents over millions of years. Deeper still, at about 2,900 kilometres down, the mantle gives way to the outer core, a shell of liquid iron and nickel that churns and flows in great convective currents. This liquid metal ocean generates Earth's magnetic field through a process called the geodynamo, creating the invisible shield that deflects solar wind and cosmic radiation, making the surface habitable, allowing compasses to point north. And at the very centre, beginning about 5,000 kilometres beneath our feet, lies the inner core itself, a sphere roughly 1,200 kilometres in radius, a ball of metal compressed by more than 3.3 million times atmospheric pressure and heated to temperatures approaching those on the Sun's surface, somewhere around 5,000 degrees Celsius. For decades, scientists have known that the inner core is solid, while the outer core remains liquid, a fact established through the careful analysis of seismic waves that travel through the planet after earthquakes. These waves come in different types: primary waves that compress and expand material as they pass, and secondary or shear waves that move material sideways, perpendicular to their direction of travel. Shear waves can only propagate through solid materials. Liquids and gases cannot support this sideways motion, so their presence tells us that the inner core must be solid. But here's where the puzzle begins, the mystery that has quietly troubled geophysicists for generations. When seismic waves pass through the inner core, they behave strangely. The shear waves move unusually slowly, much slower than they should if the inner core were made of the solid iron that pressure and temperature conditions would suggest. Scientists measure something called the Poisson's ratio, which describes how much a material bulges sideways when you compress it lengthwise, essentially a measure of how rigid or soft something is. Steel has a Poisson's ratio around 0.3, indicating it's quite stiff. Rubber has a ratio closer to 0.5, nearly incompressible, very soft and squishy. The inner core's Poisson's ratio, as calculated from seismic data, sits around 0.44 to 0.45, much closer to butter than to steel. How can something be definitively solid, proven so by the very existence of shear waves passing through it, yet behave with the softness of a substance that seems almost ready to yield? Various theories have been proposed over the years. Perhaps there's partial melting at the boundary between the inner and outer core, tiny pockets of liquid trapped in the solid matrix. Perhaps the iron takes on an unusual crystal structure under such extreme conditions, one that happens to be mechanically softer. Perhaps the inner core contains significant amounts of lighter elements, silicon, oxygen, sulfur, carbon, hydrogen, that weaken the iron framework in ways we don't fully understand. Each explanation had its merits and its problems, and none quite satisfied all the observations. Then, several years ago, computer simulations began suggesting a radical possibility. What if the inner core exists in a superionic state? The term sounds exotic, almost science fictional, but the concept is actually quite elegant. In a superionic material, different components behave differently under the same conditions. The heavy atoms, in this case iron, maintain a solid crystalline lattice, a regular three-dimensional arrangement that gives the material structural integrity. But the light atoms, carbon, perhaps hydrogen or oxygen, don't lock into fixed positions in that lattice. Instead, they slip through the gaps between iron atoms, diffusing rapidly, almost as if they were liquid, moving through the solid framework like water seeping through a rigid sponge. This hybrid state, both solid and liquid depending on which atoms you're watching, had been observed in some materials at relatively modest conditions in laboratories. Certain ionic compounds, when heated, enter superionic phases where one ion type remains fixed while another becomes mobile. But could this really happen in Earth's core, under conditions so extreme that no laboratory could easily reproduce them? The computer simulations suggested yes, but simulations are just mathematical models, approximations of reality. They're powerful tools for exploration, but they need experimental confirmation to become convincing evidence. That confirmation has now arrived, emerging from a series of careful experiments conducted in China by a team led by researchers Yuzhen Zhang, Yuqian Huang, and Yu He. Their work, published in late 2025, represents the culmination of years of development in high-pressure physics techniques, and it brings us as close as human technology can currently get to recreating inner core conditions in the laboratory. The experimental setup is deceptively simple in concept, but extraordinarily difficult in execution. The researchers start with tiny samples of iron-carbon alloy, carefully prepared to contain about 5 to 7% carbon by weight, roughly the amount scientists believe might exist in Earth's inner core based on various lines of evidence. These samples are smaller than grains of rice, precisely machined, and mounted in a target chamber. Then comes the challenge. How do you generate the conditions of the inner core? Pressures exceeding 1 million atmospheres, temperatures of thousands of degrees, for long enough to take meaningful measurements? The answer is shock compression, a technique that has revolutionized our ability to study materials under extreme conditions. A projectile accelerates down a gun barrel to speeds around 7 kilometers per second, fast enough to cross the length of a football field in less than 1/10 of a second. When this projectile impacts the target, it generates a shock wave, a sudden, violent compression that propagates through the material at supersonic speeds. For a few microseconds, the region behind the shock front reaches pressures around 140 gigapascals and temperatures near 2600 Kelvin, conditions comparable to those near the boundary between the inner and outer core. During those brief microseconds, the real work happens. High-speed diagnostics, operating at nanosecond timescales, measure how fast sound waves travel through the shocked material. Specifically, they measure the velocity of shear waves, those same sideways moving waves that seismologists use to study the inner core from afar. The researchers also run sophisticated molecular dynamics simulations in parallel, calculating how individual atoms should behave under these conditions and comparing the computational predictions with experimental measurements to build a complete picture of what's happening at the atomic scale. The results were striking. When the iron-carbon alloy was shocked to inner core-like conditions, the researchers observed a dramatic change in its properties. The shear wave velocity dropped significantly, about 20 to 25% lower than what you'd expect for pure iron under the same conditions. The calculated Poisson's ratio rose to between 0.43 and 0.45, remarkably close to the values seismologists have been measuring for the actual inner core. The material was still unambiguously solid, still capable of supporting shear waves, but it had become mechanically much softer, exhibiting exactly the kind of butter-like behaviour that has puzzled scientists for so long. The atomic scale simulations revealed what was causing this softness. Under the extreme pressure and temperature of the experiment, the iron atoms maintained their crystalline order, forming a body-centred cubic lattice, the same structure iron prefers at inner core conditions. But the carbon atoms behaved very differently. Instead of occupying fixed positions in the iron lattice, they began to diffuse rapidly, hopping from one interstitial site to another, flowing through the iron framework with diffusion coefficients comparable to those of liquids. One researcher described it as a frozen structure with flowing components, like a crowded room where the walls and floor stay fixed, but people weave continuously through the space. The dancing carbon atoms effectively soften the material, reducing its shear modulus, its resistance to deformation, without destroying its overall structural integrity. This is the Superionic state, no longer just a theoretical possibility, but an experimentally verified reality for iron-carbon alloys under inner core conditions. And crucially, the properties of this Superionic phase match what we observe seismically for Earth's actual inner core. The slow shear waves, the high Poisson's ratio, the surprising softness, all of these can be explained naturally if the inner core exists in this hybrid state, with its iron framework solid, but its light elements mobile. The implications ripple outward from this discovery like waves from a stone dropped in still water. For decades, seismologists have been seeing these unusual properties, but lacked a convincing explanation. Various models were constructed, each requiring assumptions that seemed uncomfortable or incomplete. The Superionic model doesn't require partial melting, which would have other seismic signatures we don't observe. It doesn't require exotic crystal structures that seem thermodynamically unlikely at core conditions. It simply requires the presence of light elements, which we already knew must be there based on the inner core's density being slightly lower than pure iron would produce, and the physics that naturally emerges when those light elements are subjected to extreme pressure and temperature. But understanding what the inner core is made of, and how it behaves, opens more than just a simple mystery about seismic wave speeds. Changes how we think about the entire deep Earth system, particularly about one of the planet's most essential features, the magnetic field that surrounds us, invisible but vital. Earth's magnetic field is generated in the liquid outer core through the geodynamo process. Electrically conductive liquid iron moves in complex convective patterns, driven by heat escaping from the core and by the compositional changes that occur as the inner core grows. As the planet slowly cools over geological time, iron crystallizes onto the inner core's surface, releasing latent heat and preferentially incorporating iron while rejecting lighter elements, which rise buoyantly into the outer core. These heat and compositional currents combined with Earth's rotation generate the electric currents that create the magnetic field. The inner core has always been thought to play a supporting role in this process, essentially acting as a heat source and a chemical reservoir. But if the inner core is superionic, its role becomes more active and interesting. The rapid diffusion of carbon and other light elements through the iron lattice means that the inner core isn't simply a passive lump of cooling metal. Instead, it's an active participant in chemical transport. Light elements can migrate within the inner core, potentially creating concentration gradients, generating their own buoyancy forces, contributing energy to the overall system through the work done by atoms moving through the lattice. This atomic scale churning within the supposedly solid inner core could affect how heat escapes from the deep interior, how quickly the inner core grows, and how efficiently the geodynamo operates. The researchers suggest that the Superionic state might help explain some puzzling observations about the magnetic field's strength and variability over time. It adds another energy source to the system, another way for the planet to transfer heat and power, the currents that generate our protective magnetic shield. This shield is not merely decorative. Without the magnetic field, Earth's atmosphere would be exposed directly to the solar wind, that constant stream of charged particles flowing from the sun. Over geological time, this exposure would strip away significant portions of our atmosphere, particularly the light elements, leaving the planet more like Mars, a world that lost its magnetic field billions of years ago and subsequently lost much of its atmosphere and surface water. The magnetic field makes Earth habitable, and the magnetic field depends on the core remaining active, on heat continuing to escape, on convection continuing to drive the geodynamo. If the inner core is superionic, then our models of how long this system can remain active need to be updated. The additional energy available from atomic diffusion, the more complex heat transport mechanisms, the possibility of convection within the supposedly solid inner core, all of these factors feed into calculations about Earth's long-term thermal evolution. How long will the core remain hot enough to drive convection? How long will the magnetic field persist? The Superionic model doesn't suggest any immediate changes or causes for concern. Rather, It improves our understanding of the mechanisms that have kept the system stable for most of Earth's 4.5 billion year history, and suggests it can continue doing so well into the future. There's a deeper implication here about the nature of matter under extreme conditions. The Superionic state challenges our everyday intuitions about solids and liquids being distinct, separate phases. We're used to thinking in binary terms. Ice is solid, water is liquid, the transition between them is sharp and obvious. But at extreme pressures and temperatures, matter behaves in ways that blur these categories. A material can be solid in its structural properties, maintaining a fixed framework, while simultaneously liquid in its dynamical properties, with components flowing freely. This hybrid behaviour is possible because pressure affects different interactions differently. It can lock heavy atoms into place while still allowing light, small atoms to slip between them. The inner core isn't the only place where superionic phases might exist. The researchers note that similar conditions could occur in the cores of other rocky planets, particularly super-Earths, those exoplanets with masses several times Earth's, but still composed primarily of rock and metal rather than gas. A planet twice Earth's mass might have core pressures significantly higher than ours, potentially creating even more exotic superionic phases. Whether such planets generate magnetic fields, how they cool over time, how long they remain geologically active, all of these questions might be answered in part by understanding the behaviour of superionic alloys. Some ice giant planets like Neptune and Uranus might have superionic water ice in their interiors, with oxygen atoms forming a crystal lattice while hydrogen ions flow through it. This would affect their heat transport, their magnetic field generation, even their internal structure and evolution. The same experimental and computational techniques being applied to Earth's core can be extended to model these other worlds, using different compositions appropriate to their formation and structure. As we discover more exoplanets and begin to characterize their properties more precisely, this understanding of how matter behaves under extreme conditions becomes crucial for interpreting observations and building realistic models. Back on Earth, the discovery also highlights the remarkable progress in experimental techniques over recent decades. 50 years ago, reaching inner core conditions in the laboratory was essentially impossible. Static compression methods like diamond anvil cells could reach high pressures, but struggled to achieve the necessary temperatures while maintaining stable conditions. For measurements, shock compression could reach high temperatures, but early experiments were crude, with limited diagnostic capabilities. The combination of advanced shock techniques, nanosecond-scale diagnostics, and powerful computer simulations has opened a new window into extreme states of matter. The experiments conducted by Zhang, Huang, He, and their colleagues represent hundreds of shots, each lasting microseconds, each carefully calibrated and analysed. The molecular dynamics simulations involve tracking millions of atoms through trillions of time steps, requiring supercomputers to solve the equations of motion and calculate the forces between particles. The convergence of experiment and simulation, each validating and informing the other, gives us confidence that we're not just observing laboratory curiosities, but revealing fundamental truths about how matter behaves deep inside planets. There's something profoundly satisfying about this kind of discovery, not because it changes our daily lives in obvious ways, but because it illuminates a hidden aspect of the world we inhabit. Few people will ever think about the inner core as they go about their day. It doesn't feature in weather reports or news headlines. It doesn't affect traffic patterns or crop yields or stock markets. And yet it's there, always, a sphere of hot metal at the centre of everything we know, compressed by the weight of the entire planet, heated by radioactive decay and primordial warmth left over from Earth's formation, slowly crystallizing as the planet cools, feeding energy to the magnetic field that makes the surface habitable. And now we know that this inner core isn't simply a static ball of frozen iron. It's a dynamic system where atoms are constantly in motion, where carbon threads through iron like a fluid through a solid framework, where the boundary between solid and liquid blurs into something more nuanced. The seismic waves that pass through it carry the signature of this motion, this softness, this hybrid state. The slow shear waves that puzzled seismologists for decades are telling us about atoms dancing in the dark, about matter behaving in ways that challenge our categories and expand our understanding. The growth of the inner core, about 1 millimeter per year, as iron slowly crystallizes from the liquid outer core, is likewise more complex than a simple solidification process. If light elements are continuously diffusing through the growing inner core, then the chemistry of its interior is constantly evolving. Carbon might concentrate in certain regions, creating variations in seismic properties that have indeed been observed, where waves travel at different speeds depending on their path through the inner core. These variations have been mapped by seismologists and attributed to various causes: differences in crystal orientation, temperature gradients, compositional heterogeneity. The Superionic model adds another mechanism to explain these: observations, the redistribution of mobile light elements over time, creating a chemically complex interior within the structurally solid sphere. There's also the question of how the Superionic state affects the boundary between the inner and outer core. This boundary, called the inner core boundary, is where liquid iron from the outer core crystallizes to form the solid inner core. It's a dynamic surface where phase changes occur continuously, where latent heat is released, where light elements are ejected back into the liquid. If the solid side of this boundary is Superionic, with carbon flowing through the iron lattice, then the interface itself might be more complex than a simple solid-liquid transition. There might be a thin layer where the Superionic state is just forming, where the carbon hasn't yet achieved full mobility, creating a gradient in properties rather than a sharp discontinuity. Seismic studies have indeed found evidence for complexity at the inner core boundary, with reflection suggesting a transition zone rather than an abrupt interface. The Superionic model provides a physical basis for understanding this transition, explaining why the boundary might appear somewhat diffuse in seismic images, even though we know a phase change is occurring there. All of this complexity, this richness of behaviour, emerges from relatively simple ingredients: iron, carbon, extreme pressure, extreme temperature, and the physics that governs how atoms interact under these conditions. There's an elegance to how nature organises matter at extremes, how the same fundamental forces that determine chemistry at the surface manifest in entirely different ways when atoms are squeezed together with such intensity that their electron clouds overlap and quantum effects become important. The experiments that revealed the Superionic nature of the inner core required pushing the boundaries of what's technically possible. Accelerating projectiles to 7 kilometers per second, measuring sound velocities in material that exists for only microseconds, synchronizing diagnostics with nanosecond precision, maintaining calibrations across hundreds of experimental shots. Each aspect required years of development and refinement. The molecular dynamic simulations required developing accurate models of how iron and carbon interact under extreme conditions, validating those models against experimental data, running simulations large enough to capture the relevant physics, while small enough to complete in reasonable computational time. This is careful, patient science, building understanding one experiment at a time, one simulation at a time, gradually converging on a picture that matches observation. It's the kind of work that doesn't produce dramatic headlines about revolutionary breakthroughs, but instead produces steady progress toward deeper understanding. And in December 2025, that understanding reached a milestone. We can now say with reasonable confidence that Earth's inner core exists in a Superionic state, and we can explain many of its puzzling properties as natural consequences of this hybrid solid yet flowing condition. The researchers involved in this work emphasize that there's still much to learn. The exact concentration of carbon in the inner core remains uncertain. Estimates range from about 1 to 7% by weight. There might be other light elements present as well: oxygen, silicon, sulfur, hydrogen. Each would affect the properties differently, and determining the exact composition requires combining seismic observations, experimental data, cosmochemical constraints from meteorites, and theoretical calculations of what compositions are thermodynamically stable. The Superionic iron-carbon model is a significant piece of the puzzle, but the full picture requires integrating many lines of evidence. There are also questions about how the Superionic state varies with position in the inner core. The pressure increases from about 330 gigapascals at the inner core boundary to about 360 gigapascals at the centre, a relatively small variation compared to the overall pressure, but potentially enough to affect the stability and properties of the Superionic phase. Temperature might decrease toward the centre if the inner core is convecting, or increase if it's conducting heat outward. We don't know for certain which scenario is correct. These variations could create regions where the Superionic behaviour is stronger or weaker, contributing to the seismic anisotropy and heterogeneity that observations have revealed. Future experiments will explore different compositions, different pressure-temperature paths, different timescales. Static compression methods are improving, potentially able to complement shock experiments by providing longer observation times at stable conditions. Seismic imaging continues to improve as more earthquakes are recorded and more sensitive instruments are deployed, gradually sharpening our picture of the inner core's structure. Computational methods advance with faster computers and better algorithms, allowing more realistic simulations of larger systems for longer times. Each advancement brings us closer to a complete understanding of Earth's deep interior, that realm that is literally at the centre of our world, yet remains more difficult to study than the surfaces of other planets. We've sent spacecraft to every planet in the solar system, landed rovers on Mars, flown probes through the atmospheres of Jupiter and Saturn. But the deepest hole ever drilled into Earth reached only about 12 kilometres down, barely scratching the crust, nowhere near the mantle, impossibly distant from the core. Everything we know about the deep interior comes from indirect observations, seismic waves, gravity measurements, magnetic field variations, laboratory experiments, and theoretical models. The fact that we can deduce so much from such indirect evidence is a testament to human ingenuity and the power of the scientific method. We cannot go to the inner core, cannot extract samples, cannot directly observe its behaviour. Yet through careful analysis of how waves propagate, how the magnetic field varies, how materials behave under recreated conditions, we can construct a detailed picture of what exists thousands of kilometres beneath our feet. And that picture now includes the understanding that the inner core is superionic, a discovery that will shape geophysics research for years to come. As evening deepens and the world settles toward night, imagine for a moment that journey downward through Earth's layers. Through the crust with its rocks and minerals, through the mantle with its slow convective currents driving plate tectonics, through the liquid outer core with its swirling metallic ocean generating our magnetic field, and finally to the inner core itself. There, in conditions we can barely imagine, at pressures that would instantly crush any material we could construct, at temperatures that would vaporize any substance at the surface, exists this sphere of iron with carbon flowing through it, solid yet internally mobile, frozen yet flowing, maintaining its structure while its components dance. This Superionic heart has been beating quietly, unchanged by human history, unaware of civilizations rising and falling on the surface far above. It was there before life emerged, before continents formed, before the atmosphere achieved its current composition. It will be there long after we're gone, continuing its slow growth as the planet cools, continuing to feed energy to the geodynamo, continuing its atomic scale motion that creates the macroscopic softness that seismologists detect. There's something deeply reassuring about understanding this hidden aspect of our planet. While we sleep, while we go about our daily concerns, while we worry about immediate problems and plan for uncertain futures, the machinery of Earth continues operating on timescales that dwarf human comprehension. The inner core grows about 1 millimetre per year, over a human lifetime, perhaps 7 or 8 centimetres, less than the length of a hand. Over 1,000,000 years, a kilometre. Over Earth's remaining lifetime, perhaps 1,000 kilometres or more, until the core has cooled enough that convection slows, the geodynamo weakens, and Earth becomes a magnetically dead world like Mars. But that's billions of years away, an incomprehensible span of time, longer than the entire history of complex life on Earth's surface. For now and for countless generations to come, the Superionic inner core will continue its patient work, its atoms flowing, its structure solid, its heat escaping upward to drive the convection that protects us. The December 2025 study that confirmed the Superionic nature of the inner core represents a culmination of centuries of geophysical investigation, from the first seismographs that revealed Earth's layered structure, through the development of plate tectonic theory that explained the surface manifestations of mantle convection, to the modern era of advanced experiments and simulations that can recreate conditions from the deep interior. Each generation of scientists builds on the work of those who came before, gradually assembling a more complete picture. And now we know. The soft heart of the planet is not simply soft, it's superionic, a hybrid state where iron stands firm while carbon flows, where solid and liquid coexist in the same material, where nature once again demonstrates that its creativity in organising matter exceeds our everyday experience and intuition. The seismic mystery that has puzzled geophysicists for decades finds its explanation in atomic scale dynamics, in the rapid diffusion of light elements through a heavy metal lattice, in physics that can now be studied in laboratories and understood through theory. As the night deepens and city lights glow softly against the dark, as mountains stand silent beneath their blanket of stars, the inner core continues its ancient routine, unknowing and uncaring, yet central to everything that makes Earth habitable. The magnetic field it helps generate deflects solar wind that would otherwise strip our atmosphere. The heat it releases drives convection that recycles Earth's crust, building mountains, opening ocean basins, maintaining the geological activity that regulates atmospheric carbon dioxide and stabilizes climate over millions of years. All of this depends on the core remaining hot and active, on heat continuing to escape, on the geodynamo continuing to operate. And now we understand better why this system has remained stable for so long, why the magnetic field has persisted through most of Earth's history despite variations in its strength and occasional reversals of polarity. The Superionic inner core, with its capacity for internal chemical transport and its additional energy sources from atomic diffusion, is part of what makes this long-term stability possible. In our daily lives, we interact with matter in forms that seem stable and predictable. Solids are solid, liquids are liquid, and we rarely encounter conditions where these categories blur. But Earth's interior exists in a regime far from everyday experience, where pressures exceed anything we naturally encounter, where temperatures rival the sun's surface, where matter behaves in ways that challenge our intuitions. The Superionic state is one of those exotic behaviours, and understanding it requires expanding our conceptual framework to include states that are simultaneously solid and liquid, depending on which component and which timescale we're observing. This is the nature of scientific progress. Taking what seems contradictory, the inner core is solid yet soft, rigid yet flowing, and finding the deeper explanation that resolves the apparent contradiction. The Superionic model doesn't discard previous understanding but refines it, adding nuance and detail to our picture of Earth's interior. It preserves what we knew. The inner core is structurally solid, capable of supporting shear waves, while explaining what we didn't understand, why those shear waves travel so slowly, why the material seems so soft. The scientists who conducted these experiments and simulations join a long lineage of researchers who have illuminated Earth's hidden interior. From Richard Oldham, who first identified the core in 1906, to Inga Lehmann, who discovered the inner core in 1936, to the many seismologists, mineral physicists, geodynamicists, and computational scientists who have built our current understanding piece by patient piece. Each contribution adds to humanity's collective knowledge about the planet we inhabit. And that knowledge, while not immediately practical in the sense of solving today's problems, enriches our understanding of our place in the universe. We live on a planet with an active, dynamic interior that has shaped and continues to shape the surface environment. The continents we stand on formed through volcanic processes ultimately driven by core heat. The atmosphere we breathe achieved its current composition partly through volcanic outgassing and biological processes, both dependent on Earth remaining geologically active. The magnetic field that protects us emerges from the core's internal dynamics. Understanding the superionic nature of the inner core is understanding one crucial piece of this integrated system. It's recognizing that even at Earth's center, even in conditions we can barely recreate in laboratories, matter follows physical laws we can discover and understand through careful observation and experimentation. It's seeing how extreme conditions can produce behaviors that seem exotic by surface standards, but are perfectly natural consequences of the same physics that governs everyday materials. As this long day ends and sleep approaches, the story of Earth's superionic inner core settles into the larger narrative of planetary science. One more mystery solved, one more piece of the puzzle found and fitted into place. Far below, in the dark and heat and crushing pressure, carbon atoms continue their endless dance through iron's solid lattice, softening the structure, enabling diffusion, contributing energy to the geodynamo, maintaining the planet's magnetic shield. The inner core grows, millimetre by millimetre, year by year, age by age, While on the surface, life continues, civilizations rise and fall, and humans gradually piece together the story of the world they inhabit. This newly discovered soft heart of the planet beats quietly in the darkness, neither knowing nor caring that it has finally been understood, holding the world together through physics and chemistry and time, a Superionic sphere at the centre of everything, solid yet flowing, rigid yet soft, forever, beyond reach yet finally within understanding, keeping its ancient vigil while we rest above, unaware of the atomic dance occurring thousands of kilometres beneath our sleeping forms, the steady pulse of diffusing elements and crystallizing iron that will continue long after tonight fades into tomorrow, and all our tomorrows fade into the deep geological time that measures Earth's slow evolution toward its distant cooling future. This newly discovered soft heart of the planet beats quietly in the darkness, neither knowing nor caring that it has finally been understood, holding the world together through physics and chemistry and time, a Superionic sphere at the centre of everything, solid yet flowing, rigid yet soft, forever beyond reach yet finally within understanding, keeping its ancient vigil while we rest above, unaware of the atomic dance occurring thousands of kilometres beneath our sleeping forms, the steady pulse of diffusing elements and crystallizing iron that will continue long after tonight fades into tomorrow, and all our tomorrows fade into the deep geological time that measures Earth's slow evolution toward its distant cooling future. The path to this understanding was neither straight nor simple, but rather wound through decades of incremental progress, false starts, and gradual refinement of both experimental techniques and theoretical frameworks. In the 1980s and 90s, when scientists first began seriously considering what light elements might exist in the core, carbon was just one candidate among several. Silicon seemed plausible based on its cosmic abundance and its presence in iron meteorites, which serve as proxies for planetary cores. Oxygen was attractive because it could explain certain seismic observations. Sulfur was proposed based on its chemistry with iron and its behaviour at high temperatures. Each element would affect core properties differently, and distinguishing between them required careful analysis. The computer simulations that first predicted superionic behaviour in the core emerged around 2015 and 2016, when computational power had finally advanced to the point where researchers could run molecular dynamics calculations long enough and large enough to observe the onset of atomic diffusion. These early simulations were exploratory, testing whether certain combinations of iron and light elements might exhibit superionic properties at core conditions. The results were intriguing but not definitive. Simulations are only as good as the models they use to calculate forces between atoms, and at extreme pressures those models involve approximations that can introduce uncertainties. What the simulations showed, however, was promising enough to motivate experimental verification. If iron-carbon alloys really did become superionic at inner core conditions, then laboratory measurements should show exactly the kind of softening, the reduction in shear wave velocity that seismologists had been observing. The challenge was creating those conditions in a laboratory setting where precise measurements could be made during the brief instant when the material reached the necessary pressure and temperature. Static compression techniques, using diamond anvil cells where a sample is squeezed between two diamond tips, can reach inner core pressures and hold them indefinitely, allowing detailed study. But heating such samples to inner core temperatures while maintaining pressure and making measurements is extraordinarily difficult. The diamonds themselves can fail, graphitizing or breaking under the combined stress of pressure and temperature. The sample is tiny, often just tens of micrometers across, making it hard to perform certain measurements, and determining the exact temperature inside the compressed sample, buried between diamond anvils and surrounded by insulation and pressure medium, involves significant uncertainty. Dynamic compression shock experiments offers a different trade-off. The conditions last only microseconds, but during that brief time the pressure, temperature and material state are relatively well characterized because they are controlled by the shock physics itself. The impact velocity determines the shock strength, which determines the pressure and temperature behind the shock front. Decades of research into shockwave physics have produced reliable equations of state that relate impact conditions to thermodynamic state. The challenge is making measurements during those few microseconds before the shockwave reverberates through the sample and the conditions change. The Zhang, Huang and He team's experiments represent the state-of-the-art in dynamic compression measurements. Their setup uses what's called a two-stage light gas gun, where hydrogen gas is first compressed by a large piston, then that compressed gas drives a smaller projectile down a barrel to extremely high velocities, much faster than conventional firearms or single-stage guns can achieve. The projectile, carrying an impactor plate, strikes the target assembly with exquisite precision in both velocity and angle, generating a planar shock wave that propagates into the sample. During the shock compression, the material undergoes a phase transition if one is thermodynamically favoured at the shock state. For iron-carbon alloys at the pressures and temperatures achieved, the iron transforms from its ambient condition structure into the body-centred cubic structure stable at inner core conditions. The carbon, dissolved in the iron lattice, must redistribute itself as this transformation occurs. In a normal solid, the carbon would occupy specific sites in the new crystal structure and stay there. In a superionic phase, the carbon begins diffusing through the iron framework almost immediately upon reaching the high-pressure, high-temperature state. The key measurement is the shear wave velocity, which requires generating and detecting shear waves inside the shocked material. This is accomplished using careful target design and sophisticated diagnostics. The target assembly includes layers of different materials that, when shocked, generate reverberating waves that include both compressional and shear components. By measuring the timing of wave arrivals at the back surface of the sample using laser interferometry techniques that can resolve motion on nanosecond timescales and sub-nanometer spatial scales, the researchers can deduce how fast both types of waves are travelling through the material. The shear wave velocity directly relates to the shear modulus, the material's resistance to shear deformation. A low shear wave velocity means a low shear modulus, which means the material is mechanically soft. The Poisson's ratio can be calculated from the ratio of compressional to shear wave velocities combined with the material's density. When the measurements showed shear velocities much lower than expected for solid iron, and Poisson's ratios around 0.44, matching seismic observations of the inner core, the researchers knew they had found something significant. But measurements alone don't reveal the atomic scale mechanism. This is where molecular dynamic simulations become essential. By setting up a computational model of iron-carbon alloy at the experimental conditions, thousands of atoms arranged in a simulation box with their interactions calculated using quantum mechanical principles implemented in efficient algorithms, researchers can watch how individual atoms move over time. The simulations showed that while iron atoms vibrate around fixed lattice sites, occasionally swapping positions with neighbours but generally maintaining the crystal structure, carbon atoms hop rapidly from one interstitial site to another, diffusing through the lattice with diffusion coefficients 10,000 times larger than iron's, essentially liquid-like motion within a solid framework. This atomic scale picture explains the macroscopic softening. When you try to shear the material, pushing layers of atoms sideways relative to each other, the rigid iron lattice resists strongly, but the mobile carbon atoms can flow out of the way, redistributing themselves to accommodate the deformation, effectively lubricating the motion. The result is a material that still supports shear. It's still solid in the sense that it has a non-zero shear modulus, but with a greatly reduced resistance compared to pure iron. The technical term is that the superionic phase has a much lower shear modulus than the normal solid phase, resulting in slower shear wave velocities and higher Poisson's ratio. The match between simulation and experiment is not perfect. It never is, given the approximations involved in both. But it's close enough to be convincing. The simulations predict shear velocities within about 10% of measured values, Poisson's ratios within a few percent, and diffusion coefficients that place the material firmly in the superionic regime. This convergence of experiment and simulation, two completely independent approaches arriving at consistent conclusions, gives the scientific community confidence that the superionic model is correct. Of course, no single study ever definitively settles a scientific question, especially one as complex as the nature of Earth's inner core. The experiments were conducted at conditions approximating the inner core boundary, where pressure is around 140 gigapascals and temperature around 2600 Kelvin. But the inner core extends from this boundary down to the centre, where pressure increases to around 360 gigapascals. Does the superionic phase persist throughout this range? Does it become stronger or weaker as pressure increases? Do other phase transitions occur deeper in the core that might change the behaviour? Current understanding, based on extending the simulations to higher pressures, suggests the superionic behaviour persists, and may even strengthen toward the centre. Higher pressure compresses the iron lattice, reducing the spacing between atoms, but paradoxically this can sometimes enhance the mobility of small interstitial atoms like carbon, because the energy barriers between different sites become more uniform. The simulations indicate that carbon diffusion remains rapid throughout the inner core, though the exact temperature profile with depth is uncertain enough that some ambiguity remains. There's also the question of other light elements. The experiments focused on iron-carbon because carbon is a likely constituent based on cosmochemical evidence, and because carbon's effects on core properties have been extensively studied. But oxygen, silicon and hydrogen might also be present. Each would contribute to the superionic behaviour in different ways. Oxygen is slightly larger than carbon and might diffuse more slowly. Silicon is larger still and might not achieve full superionic mobility. Hydrogen is smaller and might diffuse even faster. A full model of the inner core probably requires considering all of these elements simultaneously, understanding how they interact and partition between the solid inner core and liquid outer core as crystallization proceeds. Recent studies have begun exploring these multi-component systems, and the picture becomes more complex but also richer. Different light elements might segregate to different regions of the inner core based on their diffusion rates and chemical affinities. Fast diffusing elements like carbon and hydrogen might redistribute themselves relatively uniformly, while slower diffusing elements might retain concentration gradients left over from the inner core's growth history. This could create seismic heterogeneity, variations in wave velocities with position, that observations have indeed revealed, particularly a difference in seismic wave speeds along the Earth's rotation axis compared to the equatorial plane, a phenomenon called seismic anisotropy. The origin of this anisotropy has been debated for decades. One explanation involves preferred alignment of iron crystals. If iron grains grow with specific orientations aligned by flow in the inner core or by the magnetic field, and if seismic waves travel at different speeds along different crystal axes, then the bulk inner core would show directional dependence. Another explanation involves large-scale flow or deformation in the inner core, perhaps driven by the differential growth rates caused by heat being conducted away preferentially in certain directions. The superionic model adds another possibility. Perhaps light element concentration gradients created by diffusion and redistribution over time vary with direction, creating the observed anisotropy through compositional rather than structural effects. Unravelling which mechanism dominates requires combining seismic observations, experimental data on how anisotropy depends on crystal orientation and composition, and dynamic models of inner core evolution. This is frontier research, with new studies appearing regularly as data quality improves and theoretical understanding deepens. The superionic discovery doesn't close these questions, but rather reframes them, adding new possibilities to explore. The implications for magnetic field generation are particularly fascinating to geophysicists who study the geodynamo. Earth's magnetic field has existed for at least 3.5 billion years, as evidenced by magnetic signatures preserved in ancient rocks. But the mechanisms powering the geodynamo have changed over Earth's history. When the planet was younger and hotter, thermal convection, driven by heat escaping from the core, was probably sufficient to drive vigorous dynamo action. As the planet cooled, thermal convection alone might have become insufficient, and the inner core's growth became crucial. The inner core probably began crystallizing somewhere between 500 million and 1.5 billion years ago, the exact timing is debated, as the core cooled below the freezing point of iron at core pressures. Before this, Earth had a completely liquid core. The onset of inner core crystallization marked a major transition because it introduced compositional convection as an additional energy source. As iron crystallizes onto the growing inner core, light elements are expelled into the liquid outer core, creating buoyant fluid that rises, driving convection more efficiently than thermal effects alone. If the inner core is superionic, this picture becomes more nuanced. Light elements don't simply get expelled at the boundary and forgotten. They can continue diffusing within the solid inner core, potentially creating chemical gradients, potentially allowing some back diffusion from regions of high to low concentration. The inner core boundary itself might allow some exchange of elements between the solid and liquid phases beyond what simple crystallization models assume. This could affect how efficiently compositional convection operates, how much energy is available to the geodynamo, and how the magnetic field strength varies over time. Some researchers have proposed that variations in magnetic field strength over Earth's history, including periods when the field appears to have been weaker or when reversals occurred more frequently, might be related to changes in inner core dynamics. If the inner core's composition or growth rate varies, perhaps in response to changes in mantle convection, affecting how heat is extracted from the core, then the geodynamo's energy sources vary correspondingly. The Superionic model provides physical mechanisms for such variations through the additional energy associated with atomic diffusion and chemical redistribution. There's even speculation that the Superionic inner core might help explain why Earth's magnetic field reverses polarity occasionally, with north and south magnetic poles swapping positions. These reversals occur irregularly, sometimes several times per million years, other times with hundreds of thousands or millions of years between reversals. The causes are not fully understood but likely involve instabilities in the flow patterns in the liquid outer core. If the inner core's chemical state or boundary conditions change, perhaps through accumulation or depletion of certain light elements, or changes in crystallization texture, this might trigger reorganization of outer core flows that manifests as a reversal. These ideas remain speculative, requiring much more detailed modelling to test properly, but they illustrate how the Superionic discovery opens new avenues for understanding core dynamics and magnetic field evolution. The inner core is no longer just a passive solid ball sitting at the centre, but an active participant with internal dynamics that couple to outer core flows and influence magnetic field generation. Looking beyond Earth, the Superionic iron-carbon phase diagram, the map of which phases are stable at different pressures and temperatures, can be applied to other terrestrial planets. Mercury has a large iron core relative to its size, possibly containing sulfur and silicon. If conditions in Mercury's inner core, if one exists, allow Superionic behavior, this might affect whether Mercury can maintain a magnetic field despite its small size. Mercury does have a weak magnetic field, surprising for such a small planet, and understanding the core's state might help explain this. Venus is similar in size to Earth but lacks a magnetic field, or at most has an extremely weak one. This absence likely indicates that Venus's core is not convecting vigorously, possibly because the entire core is still liquid with no inner core crystallization to drive compositional convection. But Venus's interior structure and thermal state are poorly known due to the difficulty of seismic studies on a planet with no spacecraft on its surface, and a hostile environment that has destroyed all landers within hours. If Venus does have an inner core, or develops one in the future as it cools, understanding Superionic phases would be relevant to predicting its evolution. Mars had a magnetic field early in its history but lost it around 4 billion years ago, as evidenced by magnetic stripes in ancient crust, but no field today. This suggests Mars's core solidified or at least stopped convecting vigorously, shutting down the dynamo. Whether Mars has an inner core now is uncertain. Seismic data from the InSight lander suggested the core might still be entirely liquid, though interpretations are debated. If Mars does develop an inner core in the future, Superionic effects would influence how this affects any potential reactivation of a magnetic field, though this would take billions of years. The large moons of Jupiter and Saturn, worlds like Ganymede, Callisto, Europa, Enceladus, Titan, have interiors that are mostly rock and ice rather than metal, but some models suggest they might have small metallic cores. Ganymede has a magnetic field, indicating a convecting metallic core despite its small size and cold environment. Understanding extreme pressure phases of iron alloys helps constrain models of these exotic environments, where iron might coexist with water and ammonia ices under pressures intermediate between laboratory conditions and planetary cores. The real frontier, however, is exoplanets, particularly super-Earths, with masses 2 to 10 times Earth's. Such planets, if rocky, would have much higher internal pressures than Earth, potentially reaching terapascal pressures, 10 times Earth's central pressure, in the largest examples. At such conditions, new high-pressure phases of iron and other materials become stable, potentially creating core structures quite different from Earth's. Some studies suggest that at extreme pressures, iron might undergo additional phase transitions, forming structures we've never observed, with properties we can only infer from theoretical calculations. Understanding Superionic behavior at Earth-like conditions provides a foundation for extrapolating to more extreme conditions. If we know how iron-carbon alloys behave at 100 to 300 gigapascals, we can use that knowledge to calibrate models and simulations that explore terapascal pressures. The same physical principles apply: the competition between entropy favouring disorder and pressure favouring close packing, the different mobilities of different atomic species, the ways these factors combine to produce superionic or other exotic phases. Some researchers have suggested that in the most massive super-Earths, core pressures might be so high that iron itself becomes superionic, with lighter isotopes of iron diffusing through heavier ones, or with different electronic states becoming mobile while the atomic lattice remains fixed. These are speculative ideas pushing the boundaries of what we can currently model, but they're grounded in the same physics that produced the Earth core superionic discovery. As we discover more about exoplanets, measuring their masses, radii, and eventually perhaps detecting their magnetic fields, the ability to model their interiors becomes crucial for interpreting observations and understanding their evolution and habitability. The story of Earth's superionic inner core is therefore not just about our planet, but about the behaviour of matter under extreme conditions throughout the universe. Rocky planets are common, perhaps the most common type of planet, and nearly all of them have iron-rich cores. Understanding how those cores behave, what phases they adopt, how they generate magnetic fields, and how they evolve over billions of years is fundamental to planetary science as discipline. Back on Earth, the ongoing research program involves refining our understanding of the inner core through continued seismic studies, additional experiments at various compositions and conditions, and increasingly sophisticated simulations. New seismic arrays are being deployed, particularly in under-instrumented regions of the southern hemisphere, to improve coverage and resolution of inner core imaging. Techniques like seismic interferometry, which uses the Earth itself as a giant resonator, can detect subtle changes in inner core properties over time, potentially observing the effects of ongoing crystallization and evolution. Advanced experiments are probing adjacent regions of parameter space. What happens at slightly lower pressures, nearer the inner core boundary? What happens at higher carbon concentrations, or with multiple light elements present? How does the superionic transition temperature vary with composition? Each experimental campaign adds data points that constrain models and improve our ability to interpret seismic observations in terms of physical state. The simulations are advancing rapidly as well, driven by the relentless growth of computational power and the development of more accurate methods for calculating atomic interactions. Machine learning techniques are beginning to be applied, training algorithms to predict material properties from atomic structure, potentially allowing much faster exploration of composition and condition space. The goal is to build comprehensive phase diagrams that map out where different phases are stable for all relevant compositions and conditions, providing a complete reference for interpreting Earth's interior and other planetary cores. There's also increasing interest in studying the dynamics of the inner core over time, not just its instantaneous state. How does the superionic phase evolve as the inner core grows? Do chemical stratifications develop? Is there large-scale circulation within the supposedly solid inner core, driven by compositional buoyancy from light element redistribution? Some models suggest the inner core might be convecting in a solid-state manner, with material slowly rising on one side and sinking on the other over millions of years, driven by temperature or composition differences. The superionic mobility of light elements would facilitate such convection by allowing chemical equilibration without requiring actual flow of the iron matrix. These questions touch on fundamental issues in solid-state geophysics and mineral physics. How do materials deform and flow under extreme conditions over geological timescales? What is the effective viscosity of the inner core, its resistance to large-scale flow? And how does superionic behaviour affect this? Normal solids flow through mechanisms like dislocation motion and diffusion creep, processes that are extremely slow at low temperatures, but can become significant over millions of years at high temperatures. In a superionic material, the rapid diffusion of light elements adds another mechanism for accommodating deformation, and might significantly reduce the effective viscosity compared to a normal solid. If the inner core has low viscosity due to superionic effects, this has implications for how it responds to perturbations from the outer core and mantle above. The inner core is not rigidly locked in place. It can rotate at a slightly different rate than the mantle, as seismic studies have shown, and it can deform in response to gravitational and electromagnetic forces from the surrounding outer core. Understanding these couplings between different regions of the planet requires knowing the mechanical properties of each layer, and the superionic nature of the inner core enters directly into these calculations. There's a beautiful conceptual unity here. The same atomic scale physics that produces the superionic phase, the rapid diffusion of carbon through iron, affects properties at every scale, from shear wave velocities measured in kilometers per second to the effective viscosity governing deformation over millions of years, to the energy budget of the geodynamo operating over billions of years. Physical processes connect across these vast ranges of scale, and understanding the smallest, atomic motion, illuminates the largest, planetary evolution. This is characteristic of Earth science generally. Phenomena at human scales emerge from processes at atomic scales and contribute to dynamics at planetary scales. The rock cycle, where surface rocks are subducted into the mantle, metamorphose, melt, and eventually return to the surface as new igneous rocks, connects mineral-scale phase transitions to plate-scale tectonics to planetary-scale heat transport. The carbon cycle connects individual organisms fixing carbon through photosynthesis to global climate regulation over millions of years. The water cycle connects molecular-scale evaporation to planetary-scale ocean and atmospheric circulation. Understanding Earth requires this multi-scale perspective, and the Superionic inner core discovery exemplifies it. What began as a puzzle in seismic observations, waves travelling slower than expected, required experiments at microsecond timescales and simulations tracking individual atoms, ultimately revealing a phase of matter with implications for phenomena from magnetic field generation to planetary evolution over billions of years. As researchers continue exploring these connections, new questions inevitably emerge. Always, in science, answering one question opens several more. We now know the inner core is superionic, but this knowledge raises further puzzles. Exactly, how does this state evolve during crystallization? How do different light elements partition between phases? What role does this play in magnetic field variability? How common are superionic planetary cores throughout the galaxy? Each question motivates new research, new experiments, new observations. The cycle of discovery continues, gradually expanding the sphere of human knowledge, illuminating one small corner of the universe after another. The inner core, hidden beneath thousands of kilometers of rock and metal, inaccessible to direct observation, nonetheless yields its secrets to patient investigation, to the combination of seismic listening and experimental recreation and computational simulation that together pierce the veil of distance and extreme conditions. And through it all, the inner core itself remains unchanged by human attention, continuing its ancient processes, growing atom by atom as iron crystallizes from the liquid outer core, supporting the magnetic field that makes the surface habitable, anchoring the planet's structure, maintaining its quiet vigil at the center of our world, solid yet flowing, rigid yet soft, a superionic heart beating in the darkness, comprehended at last but unaltered by comprehension, a testament to nature's creativity in organizing matter and to humanity's capacity to understand even what lies forever beyond reach. The next story is about to begin. Please relax and enjoy. The studio lights dim to a soft amber glow, and beyond the anchor's desk stretches an infinite backdrop of stars, not the harsh twinkling points you see on a cold winter night, but something gentler, more like the sky appears when you're halfway to sleep and your eyes are just barely open. The anchor settles into their chair with the quiet deliberation of someone who has all the time in the world, adjusts a single sheet of paper that doesn't really need adjusting, and looks directly into the camera with the kind of calm that makes your shoulders drop without you realizing it. Tonight's top story is not a crisis. It is not a storm bearing down on anyone's coast, not a disaster unfolding in real time, not something that requires you to check your phone or wake your neighbour, or do anything at all except perhaps pull your blanket a little higher and let the information settle over you like snow. Tonight's story is about a visitor, a traveller from somewhere else, passing through our corner of the galaxy so quietly that if you weren't paying attention, if you weren't one of the astronomers scanning the sky each night, or one of the spacecraft drifting through the solar system with their patient cameras, you might never know it was there at all. The visitor has a name, though it's the kind of name that sounds more like a catalogue number than something you'd call a guest. 3I Atlas. The 3I tells you it's the third interstellar object we've ever confirmed, the third thing we've seen that definitely, unmistakably came from another star system and is just passing through ours on its way to somewhere else, or nowhere in particular, which is more likely. The Atlas part tells you which telescope spotted it first, back on July 1st, 2020, when the Atlas survey in Chile was doing what it does every clear night, methodically photographing the sky, comparing each night's images to the night before, looking for anything that moved, and 3I Atlas moved. Not quickly, not dramatically, but with the steady, purposeful motion of something on a long journey. Right now, as you're hearing this, is making its way outward through the inner solar system, having already swept past the Sun and Venus and Mars, now crossing through the asteroid belt on a trajectory that will bring it closest to Earth on December 19th, 2025. But closest is a relative term when you're talking about space. On December 19th, this comet, because that's what it appears to be, a comet, a ball of ice and rock wrapped in a cloud of gas and dust, will still be about 1.8 astronomical units away from us. That's roughly 170 million miles, about 270 million kilometres, almost twice the distance between Earth and the Sun. You could fit another entire Earth-Sun system in the gap between us and this visitor, with room to spare. So there's no danger, no threat, no reason to look up at the sky with anything other than curiosity or wonder, or, honestly, complete indifference if you prefer. The comet poses no risk to our planet, won't change the tides, won't affect the weather, won't do anything except be there, very far away, visible only to telescopes moving through the dark. The anchor pauses, takes a slow breath, and continues in that same unhurried cadence, the kind of voice you might hear on a nature documentary about deep-sea creatures or the formation of mountains, phenomena that unfold on timescales so vast they make human urgency seem faintly absurd. This is a story about time and distance and the remarkable fact that, very occasionally, something from another star system wanders close enough for us to see. Let's talk about who this visitor is, or what it is, since calling a comet "who" might be giving it more personality than it actually has, though after you learn a bit about its journey you might feel differently. 3I Atlas has a more official designation too, C2025N1 Atlas, the kind of label that tells other astronomers exactly when and how it was discovered. The C means it's a comet, as opposed to an asteroid. The 2025 N1 tells you it was the first such object discovered in the first half of July 2025. Astronomers divide each year into half-month periods and assign letters to them, and N corresponds to early July. The Atlas, in parentheses, credits the survey that found it, but it's that 3I prefix that makes this comet special, that elevates it from just another icy visitor from the outer reaches of our solar system to something genuinely rare. The I stands for interstellar, and the number tells you this is only the third time we've confirmed such an object passing through our neighbourhood. The first was Oumuamua, discovered in 2017, that strange elongated thing that tumbled through the inner solar system and sparked all kinds of speculation because it didn't look like anything we'd seen before. Not quite an asteroid, not quite a comet, accelerating in ways that were hard to explain with conventional physics alone. The second was 2I Borisov, found in 2019, which looked much more like a typical comet, and therefore reassured everyone that the universe wasn't necessarily full of Oumuamua-style oddities. And now we have 3 Atlas, which appears, at least so far, to be a very active, very comet-like object that just happens to be passing through from somewhere else. The anchor explains this gently, emphasizing that interstellar doesn't mean alien in the science fiction sense. No one is suggesting this is a spacecraft or a probe, or anything deliberately sent by another civilization. It means this comet formed around another star, in another planetary system, and was somehow ejected from that system millions or billions of years ago, sent wandering through the galaxy until gravity happened to steer it through our solar system now, in December 2025, while we're all going about our lives. How do astronomers know it's interstellar? How can they be so sure this isn't just a regular comet from the outer edge of our own solar system, maybe from the Oort cloud, that vast sphere of icy objects surrounding the Sun at immense distances? The answer lies in the comet's orbit, specifically in a number called eccentricity. Every orbit has an eccentricity value. A perfect circle has an eccentricity of 0. An ellipse, the shape of most planetary orbits, has an eccentricity between 0 and 1. And a parabola, the minimum energy path for something escaping a gravitational field, has an eccentricity of exactly 1. Anything with an eccentricity greater than 1 is following a hyperbola, which means it's moving too fast to be captured by the sun's gravity. It's not bound to our solar system, it's just passing through, and once it leaves, it won't be back. 3 Atlas has an eccentricity greater than 1, significantly greater. The exact value depends on the precision of the measurements, but there's no ambiguity. This is a hyperbolic orbit. The comet is moving too fast and on a trajectory too steep to have originated from anywhere within the sun's gravitational domain. It didn't get kicked out of the Oort cloud by a passing star. It didn't receive some gravitational assist from Jupiter that flung it onto this path. It came in already fast, already unbound from somewhere else. When astronomers trace its trajectory backward, projecting where it came from before the sun's gravity bent its path, they find that it points toward the direction of the constellation Sagittarius, toward the dense star fields at the centre of our Milky Way galaxy. That doesn't mean it came directly from the galactic centre. Space is vast, and the comet could have been wandering for eons, gradually changing direction as it passed through the galaxy's gravitational field. But it definitely didn't come from the plane of our solar system, the flat disk where the planets orbit. It came in from a different angle, a different origin, carrying ice and dust that formed in the disk around another star. The anchor compares 3I Atlas to its 2 predecessors, not in a way that ranks them or judges which is more interesting, but in a way that helps you understand what makes each one special. Oumuamua was the strange one, the outlier, the object that made everyone reconsider what interstellar visitors might look like. It was elongated, maybe cigar-shaped or pancake-shaped, depending on which model you believed. It had a reddish colour that suggested a surface baked by cosmic rays over millions of years. And it accelerated as it left the inner solar system, pushed by some force that wasn't quite explained by outgassing alone, though most scientists think that's still the most likely answer. Perhaps the way the gas vented from its surface created an asymmetric thrust, like a very slow, very uncontrolled rocket. Then came 2I Borisov, which looked much more familiar. It was clearly a comet, with a bright coma and a long tail, behaving just like comets from our own solar system behave when they get close to the sun. Observations showed it had a composition similar to comets we know, perhaps slightly richer in carbon monoxide, but nothing wildly exotic. Borisov was reassuring. It suggested that most interstellar objects might be ordinary comets and asteroids, just from other neighbourhoods, and that Oumuamua's weirdness might have been an exception rather than the rule. 3 Atlas seems to fall somewhere in between, or perhaps it carves out its own category. It's clearly a comet, very active, very bright, releasing lots of gas and dust. But as observations accumulate, astronomers are noticing some unusual chemical signatures, some differences in composition that hint at formation conditions unlike those in our solar system. It's not so strange as to be inexplicable, but it's not so familiar as to be boring either. It's just different enough to be scientifically valuable, just similar enough to be understandable. The scene shifts now, though there's no jarring transition, just a smooth fade to an animation that shows the inner solar system from above, like you're looking down on the sun and the planets from some vast height. The animation is slow, almost meditative, with orbits traced as pale lines, and the sun a soft yellow glow at the centre. Into this calm diagram comes 3I Atlas, its path a sharp hyperbola cutting through the orderly circles and ellipses of the planets. The narrator walks through the comet's journey with the patience of someone describing the route of a train through a countryside you've never visited, but somehow makes you want to see. 3I Atlas, approached from the southern sky, coming in on a trajectory that's retrograde, meaning it's moving in the opposite direction to the planet's orbits, but nearly in the same plane. Most comets from the Oort cloud come in at random angles, plunging through the solar system from above or below the plane of the planets. This one, though, is tilted only about 5 degrees from the ecliptic, the plane where Earth and the other planets orbit. It's an unusual geometry, one that sparked extra curiosity among astronomers. Why would an interstellar comet happen to arrive on a path so closely aligned with our solar system's architecture? It's likely just a coincidence. Space is full of coincidences, but it's a neat one. The comet's path brought it first past Mars, which it approached on October 3rd, 2025, passing within about 0.19 astronomical units of the red planet. That's roughly 18 million miles, close enough that instruments on Mars orbiters might have caught a glimpse if they were pointed the right way, though Mars doesn't have the kind of observatories Earth does. Then 3 Atlas continued inward, reaching its closest point to the Sun, perihelion, on October 29th, 2025. Perihelion is the moment when a comet gets the hottest, when solar radiation beats down most intensely on its surface, vaporizing ice and sending plumes of gas and dust streaming outward. For 3 Atlas, perihelion was at about 0.63 astronomical units, well inside the orbit of Venus, closer to the Sun than Venus ever gets. The comet would have been baking, glowing, shedding material at its maximum rate. After perihelion, it swung past Venus in early November, then began its long climb back outward, crossing Earth's orbit, not Earth itself, but the path Earth follows around the Sun, and heading toward the asteroid belt. On December 19th, it will pass closest to Earth, though as we've established, closest still means 170 million miles away, a distance so vast that even if you had the world's best backyard telescope, you'd see only a faint smudge, if you could find it at all. Then the comet will continue outward, crossing the asteroid belt, passing through the orbit of Mars again, and heading toward another close encounter, this time with Jupiter, in March 2026. That Jupiter flyby will be the comet's last major gravitational interaction with anything in our solar system. Jupiter, with its immense mass, will tug on 3I Atlas as it passes, altering the comet's trajectory slightly, giving it a small gravitational kick. But even Jupiter's gravity won't be enough to capture this visitor. The comet is moving too fast, its hyperbolic trajectory too steep. After Jupiter, 3I Atlas will sail out past Saturn, past Uranus and Neptune, past the Kuiper belt and eventually past the Oort cloud, and then it will be back in interstellar space, alone again, wandering the galaxy for millions of years until perhaps, though the odds are vanishingly small, it passes through another star system and gives some other planets' astronomers something interesting to look at. The anchor emphasises, with the same calm assurance they've maintained throughout, that despite the dramatic language you might see in some headlines, words like mysterious object or approaching Earth, the distances involved here are enormous, the encounter utterly safe. For Earth, for us, this comet is simply passing through the neighbourhood, a quiet traveller visible only to those who know where and how to look. Now comes what you might think of as the roundup segment, where the programme checks in with various observatories and spacecraft that have turned their attention to 3 Atlas. It's framed almost like a series of remote correspondents reporting from different vantage points around the solar system, though of course there are no actual correspondents floating in space. There are only instruments, cameras, spectrometers, all operated by teams of scientists on Earth, but somehow the framing makes it feel like the solar system itself is watching, paying attention to this visitor. As soon as astronomers confirmed that 3I Atlas was indeed interstellar, NASA and the European Space Agency quickly organised a coordinated observation campaign. This is what happens when something genuinely rare appears. Resources get reallocated, telescope time gets rearranged, spacecraft schedules get adjusted. Everyone wants a look. Everyone wants data. Because who knows when the next interstellar object will come through? It could be next year. It could be 50 years from now. So when one appears, you observe it while you can. Ground-based telescopes in Hawaii, Chile, Australia. Sites chosen because they have clear skies, minimal light pollution, and are spread around the world so that at least one of them always has a view of the comet as Earth rotates, began tracking 3I Atlas shortly after its discovery. They measured its brightness, watching how it changed as the comet approached the Sun and then receded. They analysed its spectrum, the rainbow of colours in its light, to identify what gases were boiling off its surface. They photographed its tail, tracking how it stretched and shifted as the solar wind pushed against it. These ground-based observations are the backbone of comet science, the steady accumulation of data night after night. But they can only see so much. Earth's atmosphere blurs fine details. Weather interrupts observations. Daylight makes half the sky inaccessible for half of every day. That's where space-based observatories come in, and that's where the story of 3I Atlas gets particularly interesting. because this comet happened to appear at a time when several spacecraft were positioned, more or less by chance, to get excellent views. The narrator likens this to a slow-moving parade, which is a gentle metaphor but also an apt one. Imagine a parade float drifting down a street so long you can't see either end, moving so slowly that each person along the route has plenty of time to watch it approach, pass directly in front of them, and then recede into the distance. 3i Atlas is the float. The observatories are the spectators. Each one gets a slightly different view, a different angle, a different moment in the comet's journey. First among these space-based correspondents is the Hubble Space Telescope, which has been orbiting Earth since 1990 and remains one of the most capable astronomical instruments ever built, despite being more than 3 decades old. Hubble has observed countless comets over the years, but an interstellar comet is special. On November 30th, 2025, Hubble turned its Wide-Field Camera 3 toward 3i Atlas and took a series of images, capturing the comet in exquisite detail. At the time of these observations, the comet was about 178 million miles from Earth, already near the distance it will have at closest approach on December 19th, just from a different angle. Hubble's images reveal several key features. There's the nucleus, the solid core of the comet. Though solid might be too strong a word, it's more like a loosely bound pile of ice and rock and dust, held together by its own weak gravity and by the stickiness of frozen volatiles. The nucleus is small, probably only a few hundred meters to a few kilometers across, too small for Hubble to resolve as anything other than a bright point. Surrounding the nucleus is the coma, a glowing cloud of gas and dust that forms when solar heat vaporizes ice on the comet's surface. The coma is much larger than the nucleus, hundreds of thousands of miles across, and it has a teardrop shape, compressed on the side facing the sun by the pressure of solar radiation and the solar wind stretched out on the opposite side into the beginnings of a tail. Hubble's images show this structure clearly: the bright condensed heart of the coma where the nucleus sits, and the more diffuse outer regions where gas and dust gradually disperse into space. But the most interesting details are the faint plumes and jets visible in the images, subtle variations in brightness that hint at active venting from specific locations on the nucleus's surface. Comets aren't uniform. Their surfaces are patchy, with some areas covered in darker, more inert material, and other areas where fresh ice is exposed. As the nucleus rotates, most comet nuclei spin, tumbling through space with periods of hours or days. Different areas get exposed to sunlight, and jets of gas and dust shoot out from these active regions. Hubble's images show at least 2 or 3 distinct jets around 3i Atlas, suggesting that its nucleus has an irregular shape and a complex surface. These observations help astronomers estimate the comet's size more precisely. By measuring how much sunlight reflects off the coma and the nucleus, and by modelling how much gas and dust the comet is releasing, they can work backward to estimate the size of the solid core. Current estimates put it somewhere between a few hundred meters and a couple of kilometers across, which is small by comet standards, smaller than the nucleus of Halley's comet, for instance, but not unusually so. It's about the size of a mountain, give or take. The narrator emphasizes gently that these observations show 3 Atlas behaving like a typical active comet despite its exotic origin. It's not doing anything strange or inexplicable, it's just following the physics of ice and sunlight and gravity, the same physics that governs all comets. The fact that this one formed around another star makes it scientifically precious, but it doesn't make it alien in any unsettling sense. Next, the program hands off to another correspondent, this one much farther from Earth. The European Space Agency's Jupiter Icy Moons Explorer, known by the acronym JUICE, is currently on a long looping cruise through the inner solar system, using flybys of Earth and Venus to gradually build up the speed it needs to reach Jupiter in the early 2030s. Right now, JUICE is in a strange sort of limbo, coasting through space with most of its instruments powered down to conserve energy, its main science mission still years away. But when an interstellar comet appears, you turn on whatever instruments you can spare. On November 2nd, 2025, as 3i Atlas was climbing back outward from perihelion, JUICE was in a position to get a relatively close look. Close by the standards of interplanetary space, anyway. The spacecraft was about 41 million miles from the comet, a distance that sounds enormous but is actually quite near compared to ground-based observations. From that range, Even JUICE's simple navigation camera, a low-resolution instrument designed mainly to help engineers on Earth figure out where the spacecraft is pointing, managed to capture a revealing image. The image is grainy, not the kind of thing you'd frame and hang on a wall, but it shows everything you need to see. There's the nucleus, a bright point-like source in the centre. Surrounding it is the glowing coma, a roughly circular halo of light. And stretching away from the nucleus, visible even in this simple snapshot, are two faint tails. A dust tail, made of microscopic particles that reflect sunlight, and a plasma tail, made of ionized gas that glows faintly as it's swept away by the solar wind. The tails are key. They're the most visually striking feature of a comet, the reason comets appear in ancient records and inspire awe. But they're also scientifically useful. The dust tail shows you the distribution of particle sizes and the rate at which material is being shed. The plasma tail shows you how the comet is interacting with the solar wind, how fast it's releasing gas, what molecules are present in that gas. From JUICE's vantage point, both tails are visible, confirming that 3I Atlas is a vigorous, active comet. The full scientific data from JUICE's instruments, higher resolution images, spectra, other measurements, will take longer to downlink back to Earth. The spacecraft's main antenna is powerful, but the data rate is slow when you're tens of millions of miles away, and JUICE has limited storage and limited windows when it can communicate with ground stations. Most of the detailed JUICE data from this flyby is expected to arrive in 2026, after it's been prioritised and queued and transmitted during scheduled communication passes. But the fact that the spacecraft managed to capture anything at all, with its simple navigation camera, during what is essentially its interplanetary commute, adds another piece to the puzzle. The tone here is patient, unhurried. There's no rush. The data will arrive when it arrives. Scientists will be analysing observations of 3I Atlas for years, comparing notes, refining models, writing papers. This is not a story with a resolution that comes next week or next month. It's a story that unfolds slowly, like the comet's own journey through the solar system. Now another observatory enters the picture, though this one doesn't take pictures at all. The XMM Newton X-ray Observatory, operated by ESA and launched in 1999, is designed to detect X-rays from cosmic sources, supernova remnants, black holes, galaxy clusters, objects so hot or so violent that they emit light at the high-energy end of the spectrum. Comets don't normally emit X-rays. They're cold, icy objects, the opposite of hot, but they can glow faintly in X-rays due to a surprising mechanism that involves the solar wind. The solar wind is a stream of charged particles, mostly protons and electrons, flowing outward from the Sun at hundreds of miles per second. When this wind encounters the neutral gas in a comet's coma, something interesting happens. Highly ionized atoms in the solar wind, atoms that have been stripped of multiple electrons by the Sun's intense heat, collide with neutral molecules in the coma and steal electrons from them. This charge exchange releases energy in the form of X-rays, creating a faint halo of high-energy light around the comet. It's a subtle effect, and detecting it requires a sensitive X-ray telescope with a long exposure time. On December 3rd, 2021, XMM Newton observed 3I Atlas for about 20 hours, staring at the comet with its X-ray cameras, accumulating photons. The goal was to measure the X-ray halo, to quantify how much gas the comet is releasing, and to probe the interaction between the solar wind and material that formed around another star. The narrator explains this in simple terms, comparing the X-ray glow to a very faint, high-pitched hiss that occurs where sunlight, solar wind, and alien ices meet. It's not something you could see with your eyes, not something that affects the comet's appearance in visible light, but it's a signature of the physical processes at work. Observing this halo can reveal details about the comet's composition, what kinds of molecules are present in the coma, how dense the gas is, how fast it's expanding outward. And because these X-ray observations are difficult and time-consuming, getting them for an interstellar comet is a rare opportunity. XMM Newton's data will also take time to analyse fully. X-ray astronomy is a specialty, requiring careful calibration and modelling to separate the faint signal of the comet from the background noise of the X-ray sky. But preliminary reports suggest the observations were successful, that the X-ray halo was detected, and that 3I Atlas is behaving once again like a typical comet. releasing gas at rates consistent with its size and distance from the Sun. The story shifts now to a slightly different angle, something closer to colour commentary than straight reporting. Observers using the Gemini North Telescope in Hawaii, along with several other ground-based facilities, have been tracking 3I Atlas's brightness and colour as it moves away from the Sun. One of the most striking findings is that the comet has become noticeably greener since passing perihelion in October. Green comets are not unusual. Many comets take on a greenish hue as they approach the Sun. But the colour is distinctive and interesting. It comes from molecules like diatomic carbon, a simple molecule made of 2 carbon atoms bonded together, which fluoresces under solar ultraviolet light, emitting a characteristic green glow. Other molecules, including cyanogen and molecular carbon, can also contribute to the green colour. The fact that 3I Atlas is getting greener as it moves away from the Sun suggests that its nucleus is still warm enough to release these gases, that it's still actively venting material even as it climbs back outward through the inner solar system. But the green colour is just the most visually obvious part of a broader set of chemical observations. A NASA-led campaign involving multiple telescopes and spectrometers has been measuring the comet's spectrum in detail, identifying the specific molecules present in its coma. The findings are intriguing. 3I Atlas appears to have a higher ratio of carbon dioxide to water than most comets in our solar system. It also shows strong emissions of nickel and iron, metals that are present in all comets but seem to be particularly abundant in this one. These differences don't mean the comet is artificial or dangerous. The narrator is careful to stress this, knowing that any mention of unusual chemistry can spark speculation. What these differences suggest, instead, is that 3I Atlas formed in a planetary system with conditions slightly different from those in our own solar system. Maybe it formed farther from its star, where temperatures were colder and carbon dioxide ice was more stable. Maybe its parent system's protoplanetary disk had a different ratio of elements, slightly more carbon or slightly more metals, due to the particular mix of materials that went into forming that star. The point is that 3I Atlas is giving us a sample of another star system's raw materials, and those materials are not quite the same as ours. It's like tasting bread from a bakery in another country, and noticing that the flour tastes slightly different. The water has a different mineral content. The bread is still bread. The comet is still a comet. But the details matter, because they tell us about the variety of conditions under which planets and comets can form. In a very gentle transition, the programme now addresses something that some viewers might have heard about, might be curious about, might even be a bit concerned about. There has been some speculation, from certain quarters, about whether 3I Atlas might be something other than a natural comet. Specifically, Harvard astrophysicist Avi Loeb, who previously proposed that 1 Oumuamua might have been an artificial object, perhaps a light sail from another civilization, has pointed out some features of 3I Atlas's trajectory and activity that he finds intriguing. Loeb has noted the comet's unusual orbital alignment, the fact that it came in nearly along the plane of our solar system's planets. He's pointed out the jets visible in Hubble's images, suggesting they might not be entirely random. He's speculated, in the careful, hedged language of a scientist who knows he's pushing boundaries, that it might be worth considering, just considering, the remote possibility that this could be a probe, a buoy, something sent deliberately. The programme treats this speculation with respect, but also with context. The narrator explains that most researchers strongly favour a natural explanation. 3 Atlas looks like a comet, behaves like a comet, has a composition consistent with comets. Its differences from solar system comets are interesting but not inexplicable. They simply reflect its origin in a different planetary system. The jets visible in Hubble's images are consistent with the kind of asymmetric outgassing that happens when a rotating, irregularly shaped nucleus exposes different patches of its surface to sunlight. The orbital alignment, while neat, is not so improbable as to demand an extraordinary explanation. Orbits are essentially random in 3 dimensions, and sometimes random orbits happen to align with interesting features by chance. The tone is calm, balanced, even generous. Science thrives on testing odd possibilities, on entertaining hypotheses that seem unlikely but can't be ruled out completely. Loeb's speculation is in that spirit. But current evidence comfortably fits an ordinary if exotic comet. The program doesn't mock the speculation, doesn't dismiss it harshly, but it also doesn't linger on it. It's one data point in a much larger story about what we're learning from this visitor. Now comes the big picture segment, the part of the program that steps back and asks why this flyby matters, why astronomers are devoting so much time and so many resources to watching what is, after all, just a small ball of ice and rock that will be gone in a few months and never return. The answer has to do with what 3I Atlas represents. A physical sample of another star's debris, a chunk of the raw materials that went into building planets around another sun. We can observe other planetary systems with telescopes. We can see the planets themselves, at least the large ones, as they pass in front of their stars or as their gravity tugs on their stars. We can analyse the light from those stars and infer what elements are present. But we can't reach out and touch anything. We can't bring a sample back to a laboratory. We can't measure the exact isotopic ratios of the ice or the precise abundances of trace metals in the dust. 3I Atlas gives us that. It's not a deliberately collected sample, not something we sent a spacecraft to retrieve, but in some ways it's even better because it's uncontaminated by human intervention. This is a piece of another planetary system that fell into our laps, and we have a few months to study it before it leaves forever. The composition of 3I Atlas can test theories about how comets form. Comets are thought to be leftovers from planet formation, bits of ice and rock that never got incorporated into planets and have been wandering the outer reaches of their star systems ever since. By comparing the composition of an interstellar comet to comets from our own solar system, astronomers can see which features are universal, presumably the result of fundamental physics and chemistry that apply everywhere, and which features are specific to particular systems, the result of local conditions like the star's temperature or the disk's initial composition. The activity level of 3I Atlas, how much gas and dust it's releasing, can tell us about the structure of its nucleus. Comets that formed in very cold conditions, far from their stars, might have preserved more of the primordial ices that were present in the protoplanetary disk. Comets that formed closer in might have lost some of their more volatile ices early on. By watching how 3I Atlas behaves as it heats up near the Sun, astronomers can infer what kinds of ices are present and how deeply they're buried. And then there's the broader statistical question. How common are interstellar objects? We've now seen 3 in less than a decade, which suggests they're passing through the solar system fairly regularly. But how regularly? Are we seeing 1 per year on average, or 1 per month, or 1 per week? The answer depends on how sensitive our surveys are, how much of the sky we're monitoring, how faint an object we can detect. As surveys like Atlas and others improve, we'll detect more interstellar objects, and the statistics will improve. Comparing the compositions and behaviours of multiple interstellar visitors will help us build a picture of what's typical and what's unusual among planetary systems across the galaxy. The narrator emphasises that these are slow, patient questions. Data from 3I Atlas will be analysed for years, fed into models, compared with data from future interstellar visitors. This is not a story with a quick resolution. It's a story that contributes to a longer, deeper understanding of how planets form, how common different types of planetary systems are, what the galaxy's inventory of small bodies looks like. The broadcast is winding down now, the lights in the studio dimming even further, the stars in the backdrop seeming to grow brighter, though that might just be a trick of perception as your eyes adjust. There's a montage, a series of slow, dreamy images that feel more like poetry than documentary. A backyard astronomer standing in a dark field, far from city lights, their telescope pointed upward at a patch of sky that looks to the untrained eye like any other patch of sky. Maybe they can see 3I Atlas, a faint fuzz through the eyepiece, or maybe they can't. Maybe the comet is too faint, too far, too diffuse. But they're looking, they're paying attention. Then Hubble, drifting silently in its orbit above Earth, sunlight glinting off its solar panels, its cameras pointed out toward the darkness where the comet glides. No sound, of course, space is silent, but you can almost imagine a hum, the whir of mechanisms, the patient clicking of data being recorded, stored, transmitted. JUICE, coasting through the inner solar system, its golden body catching the sun's light, its instruments powered down except for the ones that were briefly awakened to glimpse this visitor. It's on a long journey to Jupiter, years still ahead, but this detour, this chance encounter with an interstellar comet, is a bonus, an unexpected gift. XMM Newton, listening for X-rays in the dark, its mirrors collecting photons that have travelled from the comet's coma through the vastness of space to this telescope that orbits Earth every 2 days, sweeping across the sky in search of the high-energy universe. And finally Earth itself, turning slowly beneath a sky full of stars, continents and oceans rolling past in the light and the dark, billions of people going about their lives, most of them completely unaware that an interstellar visitor is passing by right now, this very moment, on its long, lonely journey from one star system to nowhere in particular. The host's voice returns one last time, calm and reassuring, the same voice that started this broadcast. On December 19th, they say, while most of us go about our lives, working, shopping, cooking dinner, putting children to bed, scrolling through our phones, worrying about the small concerns that fill a human day, 3 Atlas will glide past at a distance so vast that it might as well be in another world, and in a sense it is. It belongs to the space between stars, to the cold, dark stretches of the galaxy where light takes years to travel from one point to another, and where matter is spread so thin that you could sail for centuries without encountering anything at all. The comet will pass by harmlessly, leaving no mark on our planet except in the form of data, gigabytes of images, spectra, measurements, numbers in databases that astronomers will pore over for years, looking for patterns, testing theories, refining their understanding of how the universe works. It will leave a beautiful trace in our instruments, in our telescopes, in the careful observations of people who have devoted their lives to watching the sky. And then it will be gone. After the Jupiter flyby in March 2026, after the long climb outward through the outer solar system, past the orbits of Saturn and Uranus and Neptune, past the Kuiper belt where Pluto orbits, past the heliopause where the sun's influence finally fades and interstellar space begins, Thruwig Atlas will leave our solar system behind. It will be alone again, a small chunk of ice and rock tumbling through the galaxy, carrying with it no memory of this brief encounter, no record of the telescopes that watched it, or the people who wondered about it. But we will remember. We'll have the data, the images, the measurements. We'll have the knowledge that for a few months in 2025, something from another star passed close enough for us to see, and we paid attention. We turned our instruments toward it. We asked questions. We learned what we could. The final image is simple. The Milky Way stretched across a dark sky. Thousands of stars visible. The faint band of light that is our galaxy seen, edge on from our position within it. Somewhere among those stars is the one where 3 Atlas formed, though we don't know which one, and probably never will. It could have been ejected billions of years ago when its parent star was young and its planetary system was still settling into its final configuration. Or it could have been thrown out more recently, in some gravitational reshuffling, some close encounter with a passing object that sent it spinning out into the dark. Either way, it's here now, passing through our neighbourhood, a quiet traveller on an infinite journey. The studio lights fade to black, the stars remain. And somewhere, 170 million miles away and getting farther every second, a small comet continues on its way, indifferent to our telescopes, our curiosity, our wonder. It's just ice and rock and dust, following the laws of gravity and momentum, moving through space the way all things move through space, steadily, patiently, without hurry or destination. The program ends with silence, or perhaps with very faint music, something ambient and spacious, chords that resolve slowly and leave you feeling not anxious or excited, but simply aware. Aware that the universe is vast, aware that even in our little corner of it, remarkable things pass by all the time if we know where to look. Aware that tonight, as you sleep, as the world turns beneath the stars, an alien comet is making its quiet flyby, watched by patient instruments, recorded by careful observers, witnessed by a species curious enough to notice when something from elsewhere passes through. And that's all. That's the story. A visitor from another star, here for a moment, then gone. The cosmos continues. The telescopes keep watching. We go about our lives carrying the knowledge that we're not alone in the galaxy, not because we've found other civilizations, but because we've found evidence of other planetary systems, other collections of ice and rock orbiting other suns, and occasionally one of those pieces breaks free and wanders through the dark until it happens to pass by us, giving us a glimpse of what exists out there in the vast distances between stars. Sleep well. The comet is harmless, far away, on its long journey to nowhere. And we are here, safe on our planet, spinning through space as we always have. Part of something much larger than ourselves. Witnessing what we can, learning what we can, grateful for every visitor that gives us a story to tell. The next story is about to begin. Please relax and enjoy. You settle in as the studio lights dim to their gentlest setting. The kind of soft amber glow that reminds you of candlelight but steadier, more forgiving on tired eyes. Behind the anchor's desk, a backdrop slowly shifts through shades of deep blue and violet, scattered with points of white light that could be distant stars or perhaps just pleasant illusions meant to calm rather than inform. The anchor herself sits with her hands folded on the desk, papers before her that she barely glances at, and when she speaks, her voice arrives like something carried on a night breeze, unhurried and warm. Tonight's main story, she tells you, is about a single star, and though that star died long ago, its final light has only just reached our telescopes after travelling for 13 billion years through the expanding darkness of space. She wants you to know right away that this is not a story about danger or crisis, not a warning or a countdown, but simply a quiet update from the frontier of what we can see, a small addition to humanity's long list of things we have learned by looking up. The star in question exploded when the universe was only 730 million years old, which is to say it died when everything was still new, still forming, still working out the basic rules of galaxies and elements and light. The James Webb Space Telescope, our newest eye on the cosmos, caught the fading glow of that explosion, and in doing so gave astronomers the earliest confirmed supernova ever observed, a record that pushes our vision of stellar death back more than 1 billion years deeper into time than ever before. The anchor pauses to let you absorb this, her expression neutral but kind, the way someone might look at you if they were telling you about a distant relative you never met, someone whose life was lived long before you were born but whose story still matters in some abstract genealogical way. She explains that in March of this year, high-energy observatories detected a brief intense burst of gamma rays flashing across the sky, a phenomenon that happens somewhere in the universe roughly once a day, but which astronomers have learned to treat as a signpost, a cosmic flare that marks the location of something dramatic and distant. This particular burst was catalogued as GRB 24V314A, a designation that sounds clinical but which represents a moment of violent transformation, the final throes of a massive star collapsing under its own weight and releasing more energy in a few seconds than our sun will emit over its entire 10 billion year lifetime. Telescopes on the ground and in space swung into action, following the standard protocol for gamma-ray burst follow-up. They watched the afterglow, that fading ember of light that lingers after the initial flash, and they measured its properties, trying to determine how far away the event occurred and what kind of object produced it. The measurements suggested something extraordinary, a distance so great that the light had been travelling toward us since the universe was still in its infancy, and so the team requested time on the James Webb Space Telescope, the only instrument with the sensitivity and resolution to confirm what they suspected. The program now shifts, the camera pulling back from the anchor's desk and transitioning to a slow, computer-generated visualization of the James Webb Space Telescope itself, that golden hexagonal mirror floating in the blackness beyond the moon's orbit, positioned at a gravitationally stable point called L2, where it can stare continuously into deep space without the glare of Earth or the sun interfering with its vision. The narrator's voice continues, explaining in that same unhurried cadence that Webb was designed to see the universe in infrared light, wavelengths longer than visible red, and that this capability makes it uniquely suited for studying the most distant galaxies. Because as space expands, it stretches the light from faraway objects, shifting even ultraviolet and visible light into the infrared by the time it reaches us. The telescope looks fragile in the animation, its sun shields spread like golden foil, its mirrors arranged in that distinctive flower-like pattern. But you're reminded that this delicate-looking machine is among the most sophisticated instruments humanity has ever built, capable of detecting the faint warmth of a bumblebee on the moon, or more relevantly, the dying light of a star from when the universe was barely 500 million years old. Supernovae were not Webb's primary mission, the narrator notes. The telescope was built to study the first galaxies, to peer through dust clouds where stars are born, to analyse the atmospheres of planets around other stars. But its extraordinary sensitivity means that when a gamma-ray burst goes off in the early universe and someone requests follow-up observations, Webb can spot details that no previous telescope could see, including the faint smudge of a tiny galaxy and the lingering glow of a single exploding star. The visualization fades and you're taken on a conceptual journey backward through time, not with frantic urgency, but with the slow, meditative pace of someone walking you through a museum of natural history, pointing out the layers of rock and fossil that mark different eras. The narrator invites you to imagine the universe as it is now, 13.8 billion years old, filled with hundreds of billions of galaxies, each containing hundreds of billions of stars, a cosmos so vast and mature that it can seem almost static, unchanging on human timescales. Now, she says, we will rewind, not all the way to the Big Bang itself, but to a point just 730 million years after that initial moment of creation, a time when the universe was only about 5% of its current age. This was an era that astronomers call the Epoch of Rhyonisation, a name that sounds technical but which describes something fundamental, the period when the first generations of stars and galaxies were turning on, gradually filling the universe with light and energy, breaking apart the neutral hydrogen atoms that pervaded space, and creating the transparent, ionized medium through which light can travel freely today. Before this epoch, the universe was dark, a fog of neutral gas that absorbed most wavelengths of light, and after it the universe was clear, lit from within by countless stars. The supernova that Webb observed happened right in the middle of this transition, a single massive star in a small galaxy that was among the very first structures to condense out of the primordial gas, and its death would have contributed in some tiny way to the clearing of that cosmic fog, releasing energy and heavy elements into its surroundings. The narrator emphasises that catching a single star's death from this epoch is like hearing one clear note from the universe's first orchestra, a metaphor she lets hang in the air for a moment before moving on. The programme now shows you a simple infographic, animated in soft colours against a dark background, explaining what a gamma-ray burst actually is for those who might not know. These are the brightest electromagnetic events in the universe, brief flashes of the highest energy light, lasting anywhere from a fraction of a second to several minutes, and they come in two main varieties: short bursts, which are thought to result from the collision of two neutron stars or a neutron star and a black hole, and long bursts, which are associated with the collapse of very massive stars into black holes. GRB 2503.4a falls into the latter category, a long burst, and the infographic walks you through the process in gentle steps. Imagine a star at least 20 or 30 times the mass of the Sun, the narrator says, burning through its nuclear fuel at a furious rate, its core fusing hydrogen into helium, helium into carbon and oxygen, and so on up the periodic table, until it has built an iron core that can no longer sustain fusion. At that point, the core collapses catastrophically, falling inward in less than a second, and if the star is massive enough and rotating rapidly enough, the collapse can punch through to form a black hole, while simultaneously launching twin jets of material outward at nearly the speed of light. If one of those jets happens to be pointed toward Earth, we see a gamma-ray burst, a searchlight beam of high-energy photons that can outshine entire galaxies for a few seconds before fading away. The infographic fades and you return to the anchor, who explains that gamma-ray bursts are used by astronomers as cosmic signposts precisely because they are so bright and so brief. When a burst is detected, telescopes around the world and in space immediately begin observing the same patch of sky, watching for the afterglow, which is a broader wavelength emission that lingers for hours, days, or weeks, as the jet ploughs into the surrounding gas and heats it. By studying the spectrum of this afterglow, astronomers can measure how much the light has been redshifted by the expansion of the universe, and from that redshift they can calculate the distance to the source. In the case of GRB 250314a, early observations suggested a very high redshift, meaning a very great distance, and this triggered the request for Webb's involvement. The anchor describes this process not as a race or a competition, but as a careful, collaborative effort, with different teams contributing different pieces of the puzzle. The gamma-ray observatories that first spotted the burst, the ground-based optical and infrared telescopes that track the afterglow, and finally Webb, which provided the sharpest, deepest view of the host galaxy and the fading supernova. The next segment feels like a field report from deep space, though of course there is no reporter actually out there, only the data streaming back from Webb's instruments. The narration walks you through what happened after the gamma-ray burst in March. Ground-based telescopes and space-based observatories watched the afterglow over the following days, and their measurements of the spectrum revealed absorption lines from hydrogen and other elements that had been shifted far into the infrared, a clear sign that the source was extremely distant. The Webb team scheduled observations quickly, within weeks of the burst, using the telescope's near-infrared camera and its spectroscopic instruments to zoom in on the faint patch of sky where the burst had occurred. What Webb saw was a tiny host galaxy, not a grand spiral or a massive elliptical, but a small irregular cluster of stars, likely containing only a few million solar masses of material, a mere suggestion of a galaxy by modern standards. Within that galaxy, at the exact position where the gamma-ray burst had been detected, there was a point of light, faint and reddish, that matched the expected signature of a supernova's afterglow. By measuring the precise redshift of this galaxy, Webb's instruments confirmed what the earlier estimates had suggested. The light had left this star when the universe was only about 730 million years old, making this the oldest supernova ever directly observed, beating Webb's own previous record from a supernova seen at a time when the universe was about 1.8 billion years old. The narrator takes a moment to explain how astronomers confirmed that this was indeed a supernova and not some other kind of transient event, because in astronomy, it is not enough to see something bright and fading. You must also understand what you are seeing. Webb's images taken months after the initial gamma-ray burst still showed a lingering glow at the same spot, and the way this glow faded over time matched the theoretical models of a supernova, not the simpler, faster decline of a gamma-ray burst afterglow alone. Spectroscopic observations revealed the chemical signatures of heavy elements, the kind of elements that are forged in the nuclear furnace of a supernova explosion. Oxygen, magnesium, silicon, iron. These elements were not present in the universe immediately after the Big Bang. Hydrogen and helium and a trace of lithium were the only elements created in the first minutes of cosmic time. Everything heavier, everything that makes up planets and people and the chemistry of life, was made later, inside stars, and released into space when those stars died. The supernova that Webb observed was one of the very first such events, one of the earliest contributions to the cosmic inventory of heavy elements, and the fact that Webb could see it, could measure its properties, could confirm its nature, is a testament to how far our observational capabilities have come. A researcher is paraphrased as saying that only Webb currently has the sensitivity and resolution to directly show that a gamma-ray burst from such a distant galaxy came from a supernova, and you are meant to understand this not as boastfulness, but as a simple statement of fact, a recognition that this discovery was only possible because we built a telescope specifically designed to see faint, distant things in infrared light. The program now shifts to what you might call the science desk, though there is no desk, only a calm voice and simple visuals that help you understand why astronomers are excited about this discovery. The excitement, the narrator explains, comes from what this supernova can tell us about the first generations of stars, those early suns that formed from the pristine hydrogen and helium gas left over from the Big Bang. These stars, often called population 3 stars, are thought to have been different from the stars we see in the universe today, likely more massive on average, burning hotter and faster, living for only a few million years before exploding, compared to the billions of years that a star like our Sun can sustain itself. Because they contained no heavy elements to start with, their nuclear physics and their structure would have been different, and their supernovae would have been the first events to enrich the universe with carbon, oxygen, and all the other elements that later stars would incorporate. The narrator is careful to note that the star associated with GRB 250314a was not necessarily a true population 3 star. Its galaxy may have already had a few cycles of star formation, enough to contaminate the gas with trace amounts of heavy elements. But even so, it was a very early star, a representative of the first few generations, and its death gives us a data point, a quiet clue about how quickly heavy elements appeared in small newborn galaxies and how fast they began to enrich the surrounding intergalactic medium. The visuals show a simple animation of a small galaxy, just a cluster of bright points representing stars, and one of those points suddenly brightens and then fades, leaving behind an expanding shell of colour that represents the elements ejected by the supernova. The narrator explains that each such explosion seeds its environment with the building blocks of future complexity, and that over hundreds of millions of years, countless supernovae from countless small galaxies gradually turn the universe from a place of simple, pristine gas into a place where chemistry could happen, where molecules could form, where eventually planets and life could arise. This is not presented as a grand emotional narrative, but as a matter of fact, a slow process playing out over cosmic time, and the discovery of GRB 250314a is simply one more piece of evidence, one more measurement to add to the growing data set of early universe supernovae. The narrator reminds you that science often progresses not through sudden revelations, but through the accumulation of many small observations, each one refining our models, each one narrowing the range of possibilities, and this discovery is part of that patient incremental process. There is a brief recap now, a summary of what has been learned, delivered in the same calm tone that has characterized the entire broadcast. The James Webb Space Telescope has confirmed the earliest known supernova, an explosion that occurred 730 million years after the Big Bang, initially detected as a gamma-ray burst in March of this year, and later confirmed through Webb's infrared imaging and spectroscopy. This discovery breaks Webb's own previous record for the most distant supernova by more than 1 billion years of cosmic time, pushing our direct observations of stellar death back into the epoch of reionization, a critical period in the universe's history. The narrator notes that this is unlikely to remain the record for long. Astronomers expect more such discoveries as they systematically search for gamma-ray bursts and follow them up with Webb and other telescopes. The goal, she explains, is not to keep breaking records for their own sake, but to build a catalogue of early supernovae, to understand how common they were, how they varied in their properties, how they contributed to reionization and to the chemical evolution of galaxies. This is framed not as a race, but as a survey, a long-term project that will unfold over years and decades, with each new discovery adding to our understanding in small increments. The narrator mentions future plans without urgency or hype. There are other gamma-ray bursts that have been detected and are awaiting follow-up observations, and there are proposals to use Webb and other telescopes to search systematically for transient events in the early universe. The upcoming extremely large telescope, currently under construction in Chile, will have even greater light-gathering power than Webb, though it will observe invisible and infrared wavelengths from the ground rather than from space. The Nancy Grace Roman Space Telescope, scheduled to launch in the coming years, will have a much wider field of view than Webb, allowing it to survey large areas of sky and potentially catch more of these rare distant events. But all of this is described in a matter-of-fact way, as a continuation of the work that is already underway, not as a dramatic new chapter. The message is that science proceeds, telescopes improve, our catalogue of knowledge expands, and each generation of instruments opens new windows even as it answers old questions. The broadcast now begins its closing sequence, and the tone shifts subtly, becoming even more reflective, more suited to the late hour and the intended purpose of this programme, which is not to inform in the sense of delivering urgent news, but to soothe, to provide a gentle narrative that can accompany you as you drift towards sleep. The visuals show Earth from space, the globe slowly rotating, city lights glimmering on the night side like scattered jewels, and above it the stars, countless points of light that have been watching over this planet long before there were cities or lights, or anyone to look up at them. The narrator's voice invites you to imagine the James Webb Space Telescope out there beyond the Moon, beyond the orbit of communication satellites and weather satellites, and all the busy infrastructure of near-Earth space, sitting in its quiet gravitational pocket, its sunshield always oriented to block the light and heat of the sun and Earth and Moon, its mirrors always facing the other direction, out into the deep. It collects photons one by one, the narrator says, particles of light that have been travelling through space for billions of years, some of them arriving from galaxies that formed when the universe was young, some of them carrying the last light from stars that died before our solar system even existed. You're reminded that while you sleep tonight, the telescopes continue their patient work. Webb does not rest. It observes target after target, its schedule filled months in advance, with requests from astronomers around the world, each one hoping to glimpse some distant or faint or fleeting phenomenon. Ground-based observatories scan the skies for transient events, their automated systems flacking anything that appears or changes or moves, feeding data to researchers who will analyse it in the morning. The universe is not waiting for us to catch up. It continues to make and lose stars, to form and destroy galaxies, to expand and cool and evolve according to physical laws that were set in motion billions of years ago. But the pace of these changes is so slow on human timescales that the sky above your window tonight looks exactly the same as it did last night, and will look the same tomorrow night, a comforting constancy that has guided travellers and inspired poets and provided a sense of scale and wonder for as long as humans have been able to look up. The narrator brings you back to the story of GRB 250314A one last time, but now it is framed not as a scientific achievement or a record-breaking discovery, but as a single note in a vast, ongoing symphony. Somewhere in a small galaxy that no longer exists in the form it had 13 billion years ago, a massive star exhausted its fuel and collapsed, sending out a beam of gamma rays that travelled across the expanding universe, across billions of light-years of space, until finally, in March of this year, those gamma rays arrived at Earth and triggered detectors in orbit. The light from the subsequent supernova followed, stretched into the infrared by the expansion of space, faint but detectable, and Webb caught it, measured it, confirmed it. That star has been gone for 13 billion years, and the galaxy it lived in has likely merged with others, grown larger, changed shape, evolved into something we might not recognise. The supernova's ejecta, the elements it released, have long since mixed into the interstellar medium, been incorporated into new stars, perhaps even into planets, perhaps even into living things if any have arisen in that distant corner of the universe. We will never know the full story of that star or that galaxy, but we have this one snapshot, this one moment of death captured in exquisite detail, and it is enough to tell us something about how the universe worked when it was young. The final words arrive slowly, each sentence separated by a pause, each one settling into the quiet space of the studio like a soft blanket being laid over you. The universe has been making and losing stars for billions of years, the narrator says. It will continue to do so for billions more, long after our own star is burned out, long after Earth and everything on it has returned to dust. But tonight, the sky above your window is steady and familiar, the same constellations that humans have been watching and naming and telling stories about for thousands of years. One more ancient star funeral, one more supernova from the dawn of time, is simply another piece in a vast and beautiful story, a story that you are part of whether you're awake or asleep, whether you're watching telescopes or dreaming under the stars. The universe is not somewhere else, out there beyond the atmosphere and the planets and the light years of empty space. It is here. It is the ground beneath your feet and the air in your lungs and the atoms in your body, all of them forged in stars, all of them participants in this slow, unfolding process of matter, organising itself into galaxies and planets and people and thoughts. And so you can safely drift off now, knowing that the work continues, the telescopes watch, the data flows, and tomorrow or next week or next year there will be another discovery, another faint light caught after billions of years of travel, another small addition to the sum of what we know about where we came from and what the universe is like beyond the narrow slice we can see with our own eyes. The lights in the studio dim further, the backdrop of stars becomes the only illumination, and the narrator's voice fades to silence, leaving you with the image of a golden telescope in the darkness and the quiet knowledge that somewhere, always, ancient light is arriving. The silence holds for a moment, not an uncomfortable emptiness, but a spaciousness, the kind of pause that invites reflection rather than demanding it. Then the narrator's voice returns, softer now, almost a whisper, as if she is leaning in to share something more personal, more contemplative. She speaks about the nature of distance itself, how when we look at objects in deep space we're also looking backward through time, a consequence of the finite speed of light. The photons from GRB 2503A, that reached Webb's mirrors this year left their source 730 million years after the Big Bang, which means they have been travelling for more than 13 billion years, crossing a universe that was expanding all the while, stretching the space between their origin and their destination. During that immense journey, the narrator says, entire epochs of cosmic history unfolded, galaxies merged and evolved, stars formed and died in countless numbers. Our own Milky Way took shape from the slow accumulation of smaller galaxies. Our solar system condensed from a cloud of gas and dust. Earth cooled and developed oceans and an atmosphere. Life emerged and diversified and eventually produced beings capable of building telescopes and pondering their place in the cosmos. All of this happened while those photons were in transit, moving at the speed of light through the darkness, oblivious to the changes occurring around them, simply travelling in a straight line from their point of emission toward whatever might lie in their path. The visualization on the screen now shows a stylized representation of this journey. Not a literal depiction, but an artistic interpretation. A single point of light moving through a field of slowly changing shapes, galaxies appearing and growing, spirals forming, colours shifting from simpler reds and blues to more complex spectra as heavy elements become more common in the universe. The narrator explains that the universe the photons are passing through is not the same universe they left behind. The expansion of space means that distances between galaxies have grown enormously, and the wavelength of the photons themselves has been stretched, shifted from what was originally high-energy ultraviolet or visible light into the near-infrared wavelengths that Webb is designed to detect. This stretching, this redshift, is one of the most fundamental observations in cosmology, evidence for the expansion of the universe, and a tool for measuring distances to the most remote objects we can see. Without understanding redshift, the narrator notes, astronomers would have no way to determine that GRB 25034a came from the early universe rather than from somewhere much closer and more recent. The measurement of redshift is what transforms a faint smudge of infrared light into a window on the first billion years of cosmic history. The program lingers on the concept of measurement itself, the careful process by which astronomers extract meaning from the faint signals collected by their instruments. Webb's spectrographs split the light from the supernova's host galaxy into its component wavelengths, creating a spectrum, a graph that shows how much light is present at each particular colour. Within that spectrum there are features, narrow dips or peaks that correspond to specific elements absorbing or emitting light at characteristic wavelengths. Hydrogen has its signature pattern, as do helium and oxygen and carbon and every other element. By identifying these patterns and measuring exactly where they appear in the spectrum, astronomers can determine both the composition of the object they are observing and its redshift, how much the expansion of the universe has stretched those wavelengths from their rest values. For GRB 250314a's host galaxy, the redshift was large, indicating a distance corresponding to a time when the universe was very young, and the presence of various elements in the spectrum indicated that this was not a galaxy of truly primordial composition, but one that had already experienced some stellar evolution, some recycling of material through stars and supernovae. The narrator allows herself a brief aside about the human element in all of this, the astronomers who spend their careers developing the skills and knowledge to interpret these spectra, to distinguish signal from noise, to recognise patterns that might escape the notice of someone less trained. These are not people who make their discoveries in dramatic eureka moments, she says, but rather through painstaking analysis, checking and double-checking their measurements, running computer models to see if their interpretations make sense, collaborating with colleagues who might have different perspectives or expertise. The discovery of GRB 250314 involved researchers from multiple institutions and countries, people who specialise in gamma-ray bursts, in supernovae, in high-redshift galaxies, in spectroscopy, in theoretical modelling, all of them contributing their particular knowledge to the collective effort of understanding what this event means. Science, the narrator reminds you, is fundamentally a communal enterprise, built on the work of many individuals over many generations, each one adding a small piece to the edifice of knowledge that we call our understanding of the universe. The visualization shifts again, showing now a montage of other discoveries Webb has made since it began science operations, a reminder that the study of GRB 250314a is just one of many investigations the telescope is conducting. There are images of nearby star-forming regions, vast clouds of gas and dust lit from within by newborn stars, their colours enhanced to show different temperatures and compositions. There are portraits of distant galaxies, some of them familiar spiral or elliptical forms, others irregular and distorted by interactions with neighbours, or by the effects of looking back to times when galaxies had not yet settled into their mature structures. There are spectra from the atmospheres of exoplanets, planets orbiting other stars, revealing the presence of water vapour and methane and other molecules that might someday tell us whether life exists beyond Earth. The narrator notes that each of these investigations is addressing a different question about the universe, and yet they are all connected by the common thread of trying to understand how things came to be the way they are, how simple beginnings led to the complex present. The early supernova observed by Webb is part of this larger story, a piece of the puzzle that helps explain how the raw materials for planets and life were created and distributed through space. There is a momentary return to the concept of scale, the almost incomprehensible sizes and timescales involved in cosmic phenomena. The narrator invites you to consider that the supernova visible in Webb's images released as much energy in a few seconds as the Sun will radiate over its entire lifetime, and that this energy was released in a volume not much larger than Earth's orbit around the Sun. The temperatures and densities involved are so extreme that matter behaves in ways we can only approximate in our most powerful particle accelerators, and yet these conditions were once commonplace in the early universe, occurring every time a massive star reached the end of its life. The fact that we can observe these events from billions of light years away, that we can measure their properties and compare them to our theoretical models, is a testament to both the power of the physical laws that govern the universe and the ingenuity of the beings who have learned to decode the messages carried by light. The narrator's tone conveys not awe in the sense of fear, but rather a quiet appreciation, the feeling you might have when recognizing something both beautiful and profound without needing to shout about it. The programme now touches on the philosophical implications of such discoveries, though it does so lightly without heavy-handedness. The narrator suggests that there is something deeply satisfying about knowing that we can trace our own origins back through this chain of cosmic events, that the carbon in our cells and the oxygen we breathe and the calcium in our bones were all created in the hearts of stars and released into space by supernovae much like the one Webb observed, though of course much more recent and much closer to home. We are, in a very literal sense, made of stardust, a phrase that has become almost cliché but which remains true and profound. The discovery of an early supernova does not change this fundamental fact, but it does help us understand the timeline, the rate at which these stellar factories operated and the young universe, the mechanisms by which simple hydrogen and helium were transformed into the full periodic table of elements. Every time we learn more about the early universe, we learn more about the conditions that eventually made our existence possible, and while that knowledge does not answer questions of meaning or purpose, it does provide a kind of context, a sense of place in the vast sweep of cosmic history. The visualization now returns to Earth, showing familiar landscapes under starry skies, a desert at night with the Milky Way arching overhead, a forest clearing where fireflies drift among the trees beneath the constellations, a shoreline where waves reflect the light of a crescent moon. The narrator speaks about how the experience of looking up at the night sky has been part of human culture for as long as there have been humans, how ancient peoples navigated by the stars, marked time by their movements, wove them into myths and stories that explain the world and humanity's place in it. Those ancient stargazers had no idea that the points of light they watched were actually suns like ours, some of them thousands or even millions of light years away, and they certainly had no concept of galaxies, or the expansion of the universe, or the Big Bang. Yet in their own way they were engaging with the same cosmos we study today, with our telescopes and spectrographs, asking the same fundamental questions about where everything came from and how it all works. The tools have changed dramatically, the narrator says, but the impulse to understand, to look up and wonder and try to make sense of what we see remains constant across cultures and centuries. The narrator mentions, almost in passing, that the James Webb Space Telescope is named after James E. Webb, the NASA administrator who played a crucial role in the Apollo program, but who is also a somewhat controversial figure, his legacy complicated by his tenure during a time when NASA discriminated against gay and lesbian employees. This is acknowledged without dwelling on it. a recognition that scientific instruments often carry the names of flawed human beings, that progress in our understanding of the universe does not erase the injustices of the past, but rather exists alongside them, part of the complex history of how knowledge is created and by whom. The telescope itself, the narrator suggests, is now its own thing, a tool used by researchers from around the world, regardless of the politics and prejudices of an earlier era, and its discoveries belong not to any one person or nation, but to humanity as a whole. The light from GRB 254A does not care about the name painted on the telescope that captured it. It simply exists, a message from the early universe waiting to be read by whoever has the means and the curiosity to do so. The closing sequence continues, each element flowing into the next without abrupt transitions, the whole broadcast designed to guide you gently from wakefulness toward rest. The narrator speaks now about the rhythm of scientific discovery, how it is not a smooth progression, but rather a series of steps, some large and some small, with periods of rapid advancement alternating with longer stretches of incremental improvement. Webb's confirmation of the earliest known supernova is one of those steps, a significant one to be sure, but not the end of the story. There will be more observations, more distant explosions detected, more data to analyse and interpret. Some future discovery will eventually surpass GRB 250314A, finding an even earlier supernova, pushing our observations deeper into the epoch of reionization, and perhaps even to the very first stars. But that future record breaker will only be possible because of the work being done now, the techniques being refined, the instruments being built, the questions being asked. Each generation of astronomers builds on the achievements of those who came before, and in doing so makes possible the achievements of those who will come after. The stars on the backdrop behind the anchor's desk seem to brighten slightly. Or perhaps it is just that the rest of the studio has grown darker, but the effect is to draw your attention to those points of light, to remind you that they are not merely decorations but representations of real objects, each one a sun, each one potentially surrounded by planets, each one with its own story of formation and evolution and eventual fate. The narrator's voice is now barely above a whisper, each word carefully chosen and deliberately paced. She tells you that it is all right to find comfort in the steadiness of the cosmos, in the fact that despite all the violence and drama of supernovae and gamma-ray bursts and colliding galaxies, the universe as a whole operates according to consistent, understandable principles. The laws of physics that governed the behaviour of the star that exploded 13 billion years ago are the same laws that govern the behaviour of matter today, and while our understanding of those laws continues to evolve and improve, the underlying reality remains constant. There is something reassuring about this, the narrator suggests, a foundation of regularity beneath all the surface turbulence, a sense that the universe is not arbitrary or capricious, but rather follows its own internal logic, accessible to patient investigation and careful thought. The next story is about to begin. Please relax and enjoy.